Recording, no?
Oh,
Good evening, everyone. I welcome you all to this online ATAL FDP inauguration session. It will be starting soon. ಸರ್ ನೀವು ಜೂಮ್ ಮೇಲೆ ಒಂದು ನಿಮಿಷ ನೀವು ಜೂಮ್ ಮೇಲೆ ಒಂದು
Dr. Anita Devi, are you taking long time or you're starting?
It is supposed to be.
Are you starting now or you are taking little time?
ನಮಸ್ಕಾರ ಸರ್, ಕೇಳಿಸ್ತಾ ಇದೆಯಾ?
ಕೇಳಿಸ್ತಾ ಇದೆ, but they're not starting yet.
ಕೇಳಿಸ್ತಿದೆ ಸರ್, ಕೇಳಿಸ್ತಿದೆ.
I'm waiting. Please let me know when to start.
ಇಲ್ಲ, 6 to 6:30 ಅಂತ ಹೇಳಿದ್ದಾರೆ. They are trying to
We will
start.
start, sir. We are waiting for registrar to join, sir.
No, he will join
No.
soon.
ಆಮೇಲೆ ಜಾಯಿನ್ ಆಗ್ಲಿ, ತೊಂದರೆ ಇಲ್ಲ. We'll start, Professor.
Okay, sir. Okay, we will start, sir. We will start, sir.
You start. Good evening, everyone. A warm welcome to all the distinguished dignitaries, respected resource persons, esteemed faculty participants, and dear colleagues. Myself, Dr. Anita Devi, MD, Associate Professor, Department of ECE SSIT, and I'm delighted to be your host and master of ceremony for this online ATAL FDP on RTOS and automotive CAN applications. It is indeed an honor for me to guide you through the today's sessions and proceedings. On behalf of Department of Electronics and Communication Engineering, Sri Siddhartha Institute of Technology, Tumkur, it's my great honor and privilege to welcome you all to the inaugural function of 6-day online ATAL FDP on RTOS and automotive CAN applications. Embedded systems today power everything from smartphones to automobiles, and their complexity demands reliable real-time operating system for efficiency and precision. In the automotive field, the controller area network CAN protocol enables seamless communication between electronic control units, making vehicles smarter and safer. This FDP will explore how RTOS and CAN together form the backbone of advanced embedded applications. We are indeed delighted to have distinguished dignitaries, esteemed resource persons, respected family members, respected faculty members, and enthusiastic participants joining us today for this special occasion. To lead us into this space of learning and inspiration, I now invite Dr. Komala K, Associate Professor, Department of ECE, to render the invocation song. Over to you, ma'am.
ಶರಣು ಸಿದ್ಧಿ ವಿನಾಯಕ ಶರಣು ವಿದ್ಯ ಪ್ರದಾಯಕ ಶರಣು ಪಾವನ ತನಯ ಮೂರುತಿ ಶರಣು ಮೂಷಿಕ ವಾಹನ ಶರಣು 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 ಶರಣು. Thank you.
Thank you so much, Dr. Komala, for that soulful rendition. It has truly set a beautiful tone for the sessions ahead. To formally open the event, I now invite Dr. M.C. Chandrasekhar, Professor and Head, Department of ECE SSIT, to deliver the welcome address. Over to you, sir.
Respected dignitaries, esteemed deans and heads of departments, teaching and non-teaching faculty, students, resource persons, and dear participants. Good evening to all. On behalf of the Department of ECE, SSIT, it's my privilege to warmly welcome you to the inauguration of our online ATAL FDP on Advanced Embedded Systems, RTOS and Automotive CAN applications. At the outset, we respectfully remember Shikshana Bhishma, late Dr. H.M. Gangadharaya, founder, secretary of Sri Siddhartha Education Society, and late Dr. G. Shivaprasad, founder, chancellor of SAHE, whose vision continues to inspire us. We also gratefully acknowledge the support and patronage of Dr. G. Parameshwara, Honorable Home Minister, Government of Karnataka, and Chancellor SAHE. It's now my privilege to welcome our distinguished dignitaries. I warmly welcome Dr. K.B. Lingegoda, Honorable Vice Chancellor, SAHE. Sir, your inspiring leadership guides our academic journey. I extend a cordial welcome to Dr. Ashok Mehta, Registrar, SAHE. Sir, your support greatly strengthens our institutional framework. I am delighted to welcome Dr. Vivek Veeraya, Advisor to the Chancellor. Sir, your vision constantly motivates our academic community. I wholeheartedly welcome Dr. M.S. Ravi Prakasha, Principal, SSIT. Sir, your encouragement drives us towards excellence in all our endeavors. I also extend my warm welcome to our respected deans, heads of departments, our teaching and non-teaching faculty, members, and our eminent resource persons whose expertise will enrich this FTP. Above all, I am very happy to welcome the 100+ participants, around 120 to 130 participants from across the country. Your enthusiasm and active participation make this program truly meaningful. This FTP will provide valuable insights into a fast-growing field of embedded systems. I sincerely thank our coordinators, Dr. Komala K, Dr. Ghouse Ahmad Z, and students for their dedicated efforts in organizing this program. With these words, I once again extend a heartfelt welcome to all and wish for a fruitful and enriching week of learning. Thank you.
Thank you very much, sir, for your heartfelt words of welcome. Moving forward, to give us an overview of the 6-day FTP and its objectives, I invite Dr. Komala K, Associate Professor, Department of ECE SSIT, and also the coordinator of this FTP. Over to you, ma'am.
Thank you, ma'am. Very good evening, respected dignitaries, esteemed speakers, distinguished faculty members, and dear participants. We are all delighted to welcome you all to the inauguration of AICTE ATAL Faculty Development Program and RTOS Automotive and CAN application hosted in online mode. This FTP aims to equip the faculty members, researcher, the industry professional with in-depth knowledge of real-time operating system and their vital role in automotive system, especially focusing on the control area network protocol. As the automotive sector evolves with rapid technology advancement, the real-time systems and communication protocol like a CAN, foundational to ensuring the performance, the safety, and efficiency in embedded automotive applications. Through this week-long FTP, the participant will have opportunity to interact with the domain experts from the academia, research, and organization and automotive industry, who bring with them the deep expertise, practical insights, and futuristic perspectives. It is our belief that such engagements will not only enhance our teaching and research capability, but also inspire the collaborative innovation in the line with the goals of Atmanirbhar Bharat and Make in India in the domain of intelligence mobility. We extend our sincere gratitude to ASCTE Training and Learning Academy for supporting this initiative and to all the resource persons and participants for joining us. We look forward to a fruitful, enriching learning experiences. Let this FTP be the step forward in advancing knowledge, collaboration, and innovation in the field of embedded automotive system. Thank you. Once again, I heartily welcome all the participants and speakers for this inauguration function. Thank you.
Thank you, Madam, for briefing us about the FTP and its academic importance. To proceed with, we are greatly privileged to have with us Dr. K.B. Lingegowda, Vice Chancellor SAHI. I now invite him to address the gathering. Over to you, sir.
Good evening, everybody. Can you hear me now? Am I audible?
We can hear, sir.
Hello.
Yes, sir, you're audible.
Okay, thank you. Good evening, everybody. Greetings from our Sri Siddhartha Academy of Higher Education, deemed to be university with NAC A+ grade. I'm extremely happy. Though I am an ad person from medical background, unlike all of you, I'm happy to be part of this particular academic feast conducted by SSIT under the leadership of Professor Ravi Prakasha and Chandrasekhar, Komala, and all others. And this kind of academic activities should keep happening. And I'm happy that more than 100 students and staffs have registered for this particular program. And my request to all of you is, whenever you happen to visit Tumkur, kindly visit our SSIT campus to see. In fact, just to mention, just 8 days back, when Professor S.S. Iyengar from Florida International University visited, he said, nowhere in the world he has seen such kind of facilities which are available in Sri Siddhartha Institute of Engineering. So that's the reason we are extremely happy that our Honorable Chancellor, Dr. Parameshwara, is encouraging all these kind of activities. In the coming days, I'm sure we should move forward to, especially though our majority of the students are from rural background, the very mission of our founder, Dr. Gangadhar, was to reach the unreached, whether they are from rural area or from the city area. Ultimately, we have to teach them. And I wish you all the best. And from our university, we are always with you to conduct this kind of programs in the coming years. All the best. Jai Siddhartha.
Thank you, sir, for your inspiring words and valuable message. I now request Dr. M.C. Ravi Prakasha, sir, Principal SSIT, to deliver the presidential address. Over to you, sir.
Yeah. Good evening, everyone. I extend hearty welcome to all the participants and the faculty members who are online on this particular FDP. At the outset, I congratulate the coordinators, Dr. Komala and Dr. Ghouse Mohammed, for having taken up this initiative and being successful in getting it sanctioned to our college. We are really proud of the way they are doing the job, and very happy to see that the ATAL FTP has been given to us, a rare occasion for us to have good connection between colleges to other college faculty members. As you all know, ATAL FDP is mainly aimed at, is being rooted by AICTE, aimed at training and learning academy, where not only it is just a training that we are adopting through hands-on sessions, along with theory sessions by the very eminent speakers and experts in the field, but also gave a sort of platform for learning beyond the syllabus. And as you all know, we people are exposed to too much of technological changes around the world, which makes us obviously very much behind as far as our knowledge in the so-called curriculum is concerned. We need to update ourselves, equip ourselves, and see that we get the knowledge from such sources time and again to keep ourselves abreast of all the different developments that are taking place, so that we'll be very much positive and successful in reaching out to the students as to what they really require. Otherwise, as you all agree, there is always a wide gap between the industry requirements and the curriculum that we are teaching. So these are some of the very good platforms that are created by the concerned AICT and others, so that we bridge this gap to a larger extent in areas which are not really covered in full in the curriculum. And this workshop, mainly focusing on the embedded system and its applications, especially from the viewpoint of the real-time operating systems and the control area networks. I'm sure the pains taken by the coordinators to get the contacts of very eminent speakers for the next 5 days for the sessions will definitely be a very successful one, and we'll find some food for thought for all the participants. And I'm sure all the participants will find something useful once they complete the workshop. I'm sure just because it is online, the main purpose of attending this particular workshop should not be defeated. I request all the participants to be very, very sincere in attending all the classes from 6 to 9 each day and make the best use of the classes, especially the experts taking pains to come online and teach the concerned portions. I'm sure you will definitely make use of the opportunity and show interest in attending all the sessions and make the best use of the workshop. Wish you all the best. Wish the workshop all the best. Thank AICTE and the coordinators and the Department of ENC Engineering for having done this great job. Wish you all the best. Thank you very much.
Thank you very much, sir, for your thoughtful, encouraging words and motivating insights. Moving forward, to express our gratitude, I now invite Mrs. Bindu AU, Assistant Professor, Department of EC SSIT, to propose the vote of thanks. Over to you, ma'am.
A pleasant good evening to dignitaries, invited guests, knowledgeable speakers, participants, and dear colleagues. It's my pleasure to propose vote of thanks on behalf of the Department of EC SSIT on this inaugural session. My heartfelt thanks to the guest of honor of the event, Dr. K.B. Lingegowda sir, Vice Chancellor Sahe, Dr. Vivek Viraya sir, Advisor to Chancellor, Dr. Ashok Mehta sir, Registrar Sahe, for kindly accepting our invitation and motivating the organizers by gracing the inaugural session. Thank you all, sir. I sincerely thank our beloved principal, Dr. M.S. Raviprakash sir, for his guidance and encouraging leadership. Thank you, sir. My heartfelt thanks to our HOD, Dr. M.C. Chandrasekhar sir, for his support and able leadership. Thank you, sir. I thank the organizers of the FTP, Dr. Kumla K. and Dr. Ghouse Ahmad and team of EC department, and wish successful conduction of FTP. I thank all faculty and staff for their kind cooperation in smooth conduction of FTP. I thank all the participants who have shown interest for joining the FTP and hope you enjoy all the sessions of the FTP. Lastly, I would like to thank Dr. Anita Devi ma'am for her flawless mastering of ceremony. Thank you, ma'am. Over to you, ma'am.
Thank you, Bindu, for acknowledging the contributions of everyone who made this event possible. With this, we conclude the inaugural ceremony of our FTP. I once again thank our dignitaries, coordinators, faculty members, and participants for joining us today. We wish all participants a highly enriching, fruitful 6-day FDP ahead. Thank you and have a pleasant evening. So now moving forward with our program, it's time to learn more about the distinguished speaker who will be addressing us today. To formally introduce our speaker and share the remarkable profile, I now invite Hamsaleka NP, Assistant Professor, Department of ECE, to read out the biodata. Over to you, ma'am.
It is my privilege to introduce Dr. Purushottama TL, who is presently serving as an assistant professor in the Department of Electronics and Communication Engineering at Siddhaganga Institute of Technology, Tumkuru since 2013. He completed his PhD in 2023 from National Institute of Technology, Karnataka, Surathkal, in the area of passive radars and radar signal processing. Dr. Purushottama has a rich blend of academic and industry experience with 17 years in teaching and 2 years in corporate sector, having earlier worked with Cognizant Technology Solutions and Honeywell Technology Solutions, Bengaluru. He has also served as a faculty member at SDM Institute of Technology, Ujjain, and Siddhartha Institute of Technology, Tumkuru. His expertise lies in radar signal processing, passive radars, antenna design, and wireless communication. Over his career, he has taught a wide range of subjects, including digital signal processing, probability and random processes, microwave engineering, and radars for autonomous driving. Dr. Purushottama has an impressive academic record with 9 journal publications, 14 conference papers, and a patent in the field of medical and health sciences. His research contributions have earned him the prestigious IEEE Protson Award from IEEE ComSoc Bengaluru chapter. Notably, his paper at IEEE Connect 2021 was recognized as a best paper in the sensors and systems track as well as overall best paper. He has also delivered several invited talks and guest lecture at reputed institutions, inspiring students and young researchers. In addition, he has completed specialized internships and certification courses in areas such as software-defined radios, Xilinx, SOG design flow, and small satellite design. We are indeed honored to welcome Dr. Purushottama TL as today's distinguished speaker for the ATAL Faculty Development Program. Welcome you, sir. Over to
Thank
you,
you, ma'am.
sir.
Thank you.
Thank you, Hamsaleka, for that detailed introduction. So now I'll be reading out the rules for the participants. Minimum 80% attendance is mandatory. Complete the assignments, assessments, and feedback for the certificate. Join with full registered name. Keep mic muted, camera on if possible. Use only one device login. Maintain professional conduct and punctuality. Do not record sessions without permission. Same Zoom link will be used for all the days. E-certificates will be issued only on fulfilling the above requirements. I now have the privilege to invite our esteemed resource person, Dr. Purushottama TL, to deliver the session. Over to you, sir.
Thank you, ma'am. I think I'll share. I think screen is visible now.
Yeah, screen is visible.
Okay. I cannot share. Actually, a video I can turn it on once or twice whenever required. So actually, it's like background is not. I'll make it once. I think is that okay? Voice is clear, right?
Yes,
Voice
sir.
is clear.
Okay. Okay. And then I'll go to the slideshow mode. So good evening all. So mine is introduction session on automotive embedded systems and fundamentals of CAN. So actually most of the radar-based systems in the cars are comes under embedded systems only. So we worked on advanced collision avoidance systems, wherein before I actually get into the technicals. So if you have any queries like either it is technical or general, say like to slow down or to stop at some point, so you can just raise your hand or you can stop me at any stage. Even if the voice is not clear, because it depends on so many factors like internet connectivity. So I'll get it sorted. Even if any doubts are there, you can stop. And I'll proceed. So I was in, say like I was saying, advanced say collision avoidance system. So I have worked on most of the radar-based systems, especially millimeter wave radars. So we have used millimeter wave radars for target detection and tracking, and that too in autonomous vehicles. And of course, most of my work is on resolving the targets on static targets, moving targets, very fast moving vehicles, classifying, say, pedestrian classification of, say, like a moving person or a two-wheeler, then resolving the velocities of the vehicles. So radar based, not camera based. Of course, camera will not give the exact velocity with which the vehicle or pedestrian moves. So most of them falls under automotive embedded systems. And of course, CAN is like nervous system of our embedded system or any autonomous or automotive vehicles. So my presentation will run around 4 basic aspects like automotive embedded system and a bit of AutoSAR. It is like open system architecture, software architecture. And then, of course, basic communication protocol, which is controller area network. Of course, the recent version is CAN-XL, which is recently released. And will not, again, I'll not get into the depth of CAN since it is only fundamentals, fundamental introduction. I'll try to connect all the 4. So like automotive embedded systems, what is AutoSAR, why it is required, what is controller area network, and how the basic CAN protocol looks like. Then autonomous, say advanced versions of automotive embedded system like autonomous and connected vehicles. What sort of components are there in each of this, and what is what? So moving on with, let me begin with a question like, assume that you have a recent top-end car with you. So assume like even if it is voice controlled. So when you sit inside the car, you simply press, if you have a push button like, or if it is key controlled or it is voice controlled. So what all do you think happened before the engine actually comes to life? So it's not like only ignition or it's not only spark and ignition and the vehicle starts. So in fact, it's a network of small computers. So we call them as embedded systems. So they wake up, they talk to each other and make sure that car is ready and safe before even we start driving. So I am just speaking about the cars which are very recent. Say they segment the era in autonomous vehicles as 5 different segments, whichever are coming after say 2018 or at least 2017. So they are like most of the controls are, most of the control systems are electronic. So from, say, continuing from automatic braking in emergencies, say it may be a collision avoidance system, to adaptive cruise control, a vehicle which cruises on its own and maintains safer distances from the foregoing vehicles, till the display means deployment of airbags to for the driver safety. So all these are possible because of the embedded systems majorly. So I would not say entirely. So majority of the contribution in safeguarding the driver or passengers. So it is the embedded systems which are sitting inside the vehicles. So that is why it is important to learn about automotive embedded. Most of them are like, since we are deploying the sensors and radars, say, and other controllers inside the vehicle. So majority of them are for driver safety, then passenger safety. So this is more or less the introduction to the automotive embedded system. So what is an embedded system? So most of us know. So suddenly if we ask what is an embedded system? So it's just a combination of hardware and software designed for a specific function, mostly for with real-time constraints. So unlike your laptop, say basic electronic gadgets that we use, so like your laptop and cell phones that run on multiple applications, so most of the embedded systems are highly optimized for one particular application, most of the cases. So more or less, there are different ways of defining embedded systems. So one of them is it's the combination of hardware and software. So particularly designed for one particular applications. So now extending that to automotive embedded systems, it is the combination of course, the hardware and software designed for say vehicle safety, driver safety, and passenger safety, and of course the auto design especially for automobiles. So in automobiles, these embedded systems, we name them as electronic control units. So formal definition I have put up in the slides, say like a computer system that is embedded into a car to control it. So an embedded computer unit, we call it as electronic control unit. So which are, of course, we say like they are the tiny computers scattered across the vehicles. So each of them are dedicated to a particular task. Suppose I have an ECU to deploy the airbag whenever crash happens. So that ECU does its job. So whenever car or your vehicle crashes, so before the complete crash, so within millisecond it has to deploy the airbag to safeguard the driver or passengers. So these tiny computers, so basically, say they control the engines, they monitor all other tasks, they take the input from the sensors. So that inputs would be forwarded to electronic control unit. Of course, most of them are distributed centralized control unit. So then controls, so then take the decision based on the sensor inputs. So what are the examples of automotive embedded systems? Of course, we can list so many. So electronic or engine control unit, which controls the ignition fuel injection. So tire pressure monitoring system, most of the recent cars will have this. They directly displays in PPS what is the air pressure. So then adaptive cruise control, which maintains a safer distance from the vehicle ahead. Of course, most of the recent cars have rear collision avoidance also. Airbag control system, which deploys the airbags in milliseconds. So less than, to be specific, less than 20 to 50 milliseconds. So why these embedded systems? Say, of course, these are the extended, say, applications like blind spot detection in every vehicle, even especially for trucks. So they have many blind spots majorly. So most of they are radar based. So detect a vehicle within 20 meters or less, which are moving very close to the current vehicle to avoid again the collision. So most of them are usually radar based, if not camera based, because so installing the camera and taking the input from multiple directions, it is hard. But if we stare the radar antenna for a wider angle, we can cover 360-degree around the vehicle. Of course, autonomous emergency braking, cruise control, intelligence parking, say crash traffic alert. We have, say, if you consider the dashboard of a recent vehicle, there are so many features. So which comes under ADAS. ADAS stands for Advanced Driver Assistance System in automobiles. So why these embedded systems in the automobiles are so automotive? So why these automotive embedded systems? So basically you can have four basic reasons. Say like so these are like general features. So priority features, why these embedded systems? Basically for first and primary thing is safety. So you can take the best example is again airbag. So to safeguard our driver and passengers. So first primary thing is safety. Second, you can say we can list out as performance and efficiency. Say for example, you can quote engine control unit, so which will have a dedicated ECU, which monitors the fuel injection and ignition. Say for example, your vehicle is moving up a hill. So in that case, ECU senses the load on the vehicle and it adjusts the fuel injection instantly. So of course, this is the second reason, performance and efficiency. So what might be the third reason? It is the comfortness and convenience for the drivers and passengers. So lastly, of course, most recent after 2020 is your connectivity and intelligence. The example is like say we cannot say autonomous navigation. In Indian roads, very few case studies are there for autonomous navigation. So specifically for GPS, say for cruise from one location to other location, it aids us in traveling from one location to other location. So with lesser outer support. And then now they say V2X, vehicle to anything communication. So sharing the location of the vehicle, speed, and where it is traveling. So all those we call it as V2X. So vehicle to infrastructure, we call it as vehicle to vehicle, vehicle to pedestrian, vehicle to. So they treat say like massive MIMO. They treat everything around the vehicle as wireless transceivers and share the information to them. So basically, the automotive embedded systems are for 4 reasons. One is like for safety. Second is like to improve the performance and efficiency. Third is like for comfortness and convenience. Lastly, for connectivity and intelligence. So these may be the reasons. So, so this is regarding the automotive embedded systems. Prior, I take the features of automotive embedded systems. So, how many? Say, like, say, let me summarize. So, in recent vehicles, they say more than 100 ECUs, but in back in 2006 to 10, say where they call it as say level 2 of automation, there itself they had 70 to 100 electronic control unit. What are electronic control units? They are the tiny computers. Most of them have the sensor inputs or other external inputs and take the decision based on the inputs or thresholds set. So the basic features are there. These electronic control units are for energy saving and low emission, for safety, for comfortness and convenience, of course, for cost and weight reduction. So in recent vehicles, most of these ECUs are connected with in-vehicle networks. So this networking is done through CAN. So if you consider, say, as I quoted, so inside the connected vehicles, so the common, say, communication protocols that they use are, say, like, say, LIN, CAN, and FlexiRay protocols. Most of the cases, the recent version of the CAN is CAN XL. So they use CAN protocol. So now imagine like if individual ECU, say, what are electronic control unit, they have their own blocks along with the sensor connection. Sir? So, any doubts? Audible, right?
Yes, sir, you're audible.
Okay, okay. Some glitch was there. Of course, last one is like I forgot to mention reliability and safety. This standard is governed by ISO 26262. Of course, there are different numbers. I'll take in the further slides. So lastly, say I say networking and communication in vehicle communication. To quote this, let us consider if each electronic control unit is connected to a sensor and they work in isolation. Say like one electronic control unit is controlling the engine, other is handling airbags, and another is managing infotainment. So if they are not working together, say each of the ECU is connected separately in isolation, they are working in isolation to control the engine and handling different functions. How will they share the information? So suppose I'll take 2 case studies. Suppose one example is when say when the driver hits a brake, the electronic control unit say associated with brake immediately has to inform the engine control unit to cut down the torque, and also the ABS control unit has to take care of wheel locking. So if they are not working together, if they are isolated, so this will not happen. So which means all these electronic control units, which we call them as tiny computers, has to work together, has to share their information. So suppose second one is critical. Assume like airbag ECU detects a crash. So in that case, it needs the data from crash sensors, their seat belt is worn, or engine status. So within millisecond, within 20 to 30 or maximum 40 millisecond, it has to collect all this data, sample it, and take the decision of deploying the airbag. So this requires a communication between the electronic control unit spread across the vehicle. So controller area network, it is the again devised by Bosch in 1980s. So that is the basic communication protocol, which is even now it is being used. Of course, the advanced versions are like FlexiRay. So CAN is like, say, that is why I quoted in the beginning slide. So CAN is like the nervous system of the car, allowing electronic control units spread across the vehicle to communicate each other. So say this is like basic question. So forgot to mention, most of the slides are say taken from Bosch only. So again, since the source was common, I wherever required, I have mentioned like from where what source I have taken. So these are like we had attended the training. So most of the slides are taken from Bosch, say on automotive radars. So we had attended. From there, I have copied the content. So the same question was posed to us. Say if you had to design an embedded system for cars, so that must never fail. Never fail. It is again. Say if we go to the probability again, we cannot say never fail. So minimal. So which feature would you prioritize first? Reliability, cost, or performance? So of course, there is a trade-off between all the three. So everyone cannot go to a very costly car for only for safety and reliability. And of course, based on the context, we would prefer, say, we would take the balance of all the three. Say, like, of course, we prioritize reliability over performance, and of course, second comes cost. So now, say we knew like electronic control units are the basic key. So the key blocks in the controlling different parts of sensors or different sensors taking the input. So I think say the block diagram that I have shown is bit clumsy. So visible, right? So okay, right? This the block diagram that is being kept in the right hand side.
Yes, sir. Yes.
It's visible, but not exactly clear for us.
Okay, say any electronic control unit, I'll sort it out. So any control electronic control unit basically will have a power circuit, and it will have a centralized microcontroller. Of course, most of the data that it processes is digital, so it should have a to D converter, analog to digital converter, since it takes apart from key signal, gear signal, or any brake signals which are analog. So to convert it to digital, or even if it is sensor inputs, it needs A to D converter. So then for displaying and other purposes, it needs a D to A converter. So this is like VCO, vehicle control unit, or electronic control unit at its simplest form. And of course, it should have communication protocols, so like Wi-Fi enabled, Bluetooth, GPS. So most of them for say communication with the say driver, and of also for the connectivity. And then it should have a wireless extra connection to the external devices. So overall, you can segment any electronic, of course, to communicate to different say electronic control units. Say it should have say like CAN bus, say running over entire vehicular network. So basically, electronic control unit will have a microcontroller, a memory, A to D and D to A converters. Of course, it is synchronized in sync with CAN. So CAN is of course asynchronous. So the CAN bus that enables the reliable communication between various ECUs inside the vehicles. So HMI means human machine interface for control and feedback. So this is the basic block diagram of any ECU. So next is, so I'll move further. So this is a simple example of number of ECUs. I just quoted like say earlier to 2010 itself, there were so many ECUs in high-end cars. So one example is in Lexus LS460, released in September 2006. Say again, the source is from Wikipedia. Say it is mentioned like from different even news media. So more than 100 electronic control units were embedded in say when all optional, say luxury, are installed. And of course, over 7 million lines of software is embedded inside the entire system. So this is like, this is how complex in the network of electronic control units which lie in the vehicle. So now this is about the introduction to the automotive embedded systems. So we just defined what are examples of automotive embedded systems. So we just defined what are automotive embedded systems, examples of automotive embedded systems, of course, several ADAS features. So then what are the general features of automotive embedded systems? So why these automotive embedded systems are for primarily. So then next is like what is the general block diagram of electronic control unit, which is base and an example. So now next topic is classification. Of course, if you go through different technical papers, there are different classifications. So I have picked up the most generic one. Generally, so overall, we can classify the automotive embedded systems into 6 basic classes. So the embedded systems which are related to powertrain systems. So basically for engine control and transmission, fuel injection and fuel, say engine efficiency. So the basic features related to powertrain embedded systems are real-time control of engine systems. So again, depending on the context. So then transmission, fuel and emissions. So optimization of performance and fuel efficiency depending on the path that the vehicle is cruising. So examples are engine control unit, transmission control unit, and battery management systems. So second class is like chassis and safety systems. These are related to, again, they adhere to ISO standard 26262. Then it is basically primarily for safety. So again, they are like basic feature is very hard real. Say one of the example is again say airbag electronic control unit. So which has to respond within 20 to 30 milliseconds, and of course even anti-lock braking system. So they should be fault tolerant and very safer. Again, that is why they have to adhere to the standard ISO. So the number is specified. Again, examples are anti-lock braking system, airbag electronic control unit, electronic stability control. So most of them comes under ADAS features. So then tire pressure monitoring system. So the third class is body electronics. Again, it is for passenger comfort and convenience. So then again, often connected to via LIN bus, local interconnect network. So examples are like power windows. So lighting control, again, based on different context or environment. So the light, the intensity of light can be controlled. Again, keyless entry. So depending on what sensors are being deployed in the car, so this varies. Again, body electronic features vary. So next further classes are like you can segment these into infotainment and telematics. So this is for driver information and entertainment, of course with connectivity. How do you say this comes under human machine interface? So interfaces with again smart and then cloud, say data handling, real time data exchange, and of course most of these things comes under entertainment, say infotainment. So one is like GPS navigation whenever we are cruising from say one location to other location. So then say this helps us. So then telematics control unit, and of course the heads up display. So next class is ADAS. So again, say ADAS, I would say level 1 to level 5. If you consider level 5, it has nearly 8 to 10 radars installed in the single car for 360-degree view around the car. So it is for say again enhances the safety most of the cases. So 360-degree vision around the vehicle, basically it is for safety, and of course it requires the communication protocol CAN-FD. CAN-FD, FD stands for flexible data rate. So the examples are like adaptive cruise control, lane departure warning, automatic emergency braking, blind spot detection. So nowadays, most of them are radar based. Even adaptive cruise control, they use FMCW radars. Lane departure warning also, they use the combination of say lidar and radars. Automatic emergency braking, most of the cases it is lidar and radar. Blind spot detection, they use FMCW radar. So in recent cars, after on-chip radars are made available, so most of the ADAS features are radar based, and of course they integrate camera wherever classification or detection is required. So the last class is like electric and hybrid vehicle systems. So these are to manage high voltage batteries, safer charging and discharging. So they come under battery management system. Again, it depends on vehicle load. So then optimize the regenerative braking and energy usage. So the examples of electronic control unit, say responsible for this electric and hybrid vehicle systems are BMS, so electric device control unit, regenerative braking, and onboard charger. So overall, say again, in different papers, they have classified in different ways. I've combined them and I've formed into 6 segments. So powertrain systems, chassis and safety systems, body electronics, infotainment, ADAS, and of course electric and hybrid vehicle systems. So this is the classification of automotive embedded systems. Of course, I've taken few examples related to control units and automotive embedded systems. So the first example is like anti-lock braking system. So what is the function of anti-lock braking system? Whenever the speed of the car, whenever it is overspeeded, say the rotational speed of the wheel has to be monitored. If some skid is detected, so it has to control the hydraulic pressure to the brake and say reduce or stop the skidding. So this system is relatively simple, but in recent vehicles, so again it is becoming complex. Of course, assume like this is the ABS control module. So these are like hydraulic pumps and valves. So wheel speed sensor, say detects in most of the recent cars, it will have speeds being displayed under ADAS. So it detects the speed, so senses it, sends it to the electronic control unit responsible for ABS. So and avoids the anti-lock braking, say avoids the skidding of the vehicle. So the safety requirement is like continuous reduction of hydraulic pressure, so which causes non-braking. So the second example is like most common example. So airbag control system. Of course, the response time is very less. So the trigger must be within 10 to 20 millisecond. So it monitors various sensors, say like starting from accelerometer or even seat belt. So if collision is detected, so it has to deploy the airbags to for driver safety. So it has to inflate a bag. So the third case or example that I have taken is adaptive cruise control. Say most of them, say as indicated in the image, it is radar based. So you can see the look at the block diagram of the entire control system. So basically, sensors are like radar sensors. It collects the information, sensor information, say sends it to again most of the cases the this type of control system will have multiple microcontrollers. So that is why it is mentioned like upper controller and lower controller. So that sends it to the controller. So of course it compares that to a threshold. Say again, what is the safer distance at which the opposite vehicle can cruise? So that will be compared. So depending on what value is being say compared, so desired deceleration will be sent to different control unit, which is responsible for deceleration of the vehicle. Of course, if that crosses a limit, so even say the electronic control unit can take over. So that is in the recent vehicles, it can take over the driver and it can halt the vehicle. So this is like third case study. So this will be fed to the main central controller, so which takes the necessary action. Of course, other examples of the embedded systems are control units, which are responsible for different applications are So like automatic parking, vehicle platooning, so driver drowsiness detection system. Most of this is either camera based or radar based. Vehicular communication system, of course, forward or rear collision avoidance system, and then lane departure warning system. So this is regarding, say, the automotive embedded systems. So basically till here, so we just define what are automotive, say, embedded systems, what are their basic features, why do we need automotive embedded systems. So generally, how do we classify the automotive embedded systems? Some examples of, say, standard automotive embedded systems. Of course, they have mentioned automotive systems. So specifically, I have taken automotive embedded systems. So I'll take a 1 minute, say, halt here. So audible, right? Throughout these slides, any glitches in the audibility, or of course, apart from this block diagram, I think most of the images are clear. So is it okay, right?
Yes, sir, audible.
So
Yes, sir. Even the block diagram was visible. We can able to zoom it up and we can just, observe each and every blocks over there.
okay, thank you. So I'll take 30 seconds break before I move on further. So next is like requirements on in vehicle, say like requirements for the networks, and so we just completed automotive embedded systems. So next are like so how about networking, and then how about the standard RTOS? So I'll proceed. So what are the requirements on in-vehicle networks? Say like we have so many embedded systems inside a single vehicle. Say like chassis network. Say we mentioned infotainment, ADAS, so safety. So what are the basic requirements? So I have mentioned three of them. I have handpicked. So if you consider chassis network, what was like chassis network? So like chassis and safety, they are for say response time is very less. They should be fault tolerant, and examples are these. So in that case, what are the requirement for in-vehicle network? So in the networking, so what should be guaranteed? So it is like short and guaranteed response time. And of course, most of the cases they are for warnings or emergency. So in that case, say they are like small, the size of the data that we communicate is small size. And of course, they should be highly reliable. So this is like requirement for say chassis network. So then if we consider body electronics network, so most of the cases, it is like say a large number of network nodes or sensor nodes. Say even if it is reliability is moderate, so the power consumption should be less, because the number of network nodes are more, even the number of sensors are more, the data that is exchanged is high. So that is why for body electronics network, so the requirement is like lower power consumption. So next, if we consider multimedia network, so the bandwidth that is required, so because so nowadays even video is being live streamed. So in that case, the bandwidth required for multimedia data, audio and video basically, so it is of very high bandwidth, and of course moderate reliability. So only if most of the cases multimedia is for infotainment. Of course, the cruising, say it is like say GPS, car navigation system. So that requires higher bandwidth for multimedia data. So these are like some requirements for in-vehicular network. So wherever there are multiple ECUs which are deployed for different applications. So then say for them to communicate, so the basic requirements are different for different aspects. So just to illustrate that, so this slide, in this slide we have summarized this. For example, say again, we consider the criticality, that should be highly reliable, again shorter response time, so chassis network. So then for communication, So again, larger bandwidth is required. Again, larger computing power is required. So of course, the dynamics, vehicle dynamics, say there is again another segment or say another network inside. Say we call it as vehicle dynamics integrated management system. So basically, it is for controlling brakes, steering control, engine for avoiding slip and spin. So this is for electronically controlled brake systems. Again, engine ECU. So this is basically for vehicle dynamics. So again, example. So further, say it is not current problems. It's a very old. Say again, not old. Older in the sense, say to be specific, 6 years back. So these are listed out at that time again. So the current problems in automotive embedded systems are like complicated system design, considering different networks. So each of the say feature that you need in the vehicle, they are adding up the sensors. So in that case, the system design is very complex. So again, integration, again integrating them to the corresponding ECU and the basic network is again becoming complex. That increases the deployment cost, time, and again they have to be highly reliable and safer. Again, large scale and complicated software. Again, say again, nowadays like connected vehicles are coming into picture, so it has to be safety aspect has to be considered. So that is why how to use or reuse the existing software, that also matters. Again, there are too many large number of electronic control units. Say at the end, I'll show you the recent dashboard. Each of the feature that is being displayed in the dashboard, say most of the cases they are embedded. So in that case, there are too many a large number of electronic control units to manage. So again, insufficient space inside the car, and the network is becoming very complex. So increasing design complexity. So these are the say again current problems. Again, if not current, so they are managing. So they are the data is like 6 years old. So again, I think this should have been the previous slide. So pre-crash safety system again. Uh, so this is for autonomous vehicles. So what are the different pre-crash sensors that they use? So you can say like driver monitoring camera, stereo camera, say then millimeter wave radar. So this is like more or less the another example for electronic control unit or electronic control system, which is for safety. Say comes under safety network. So actually, I'll consider this slide. So as we consider, say, more number of sensors, more number of electronic control unit being deployed, or for say either it may be for safety or maybe for infotainment or maybe for advanced driver assistance system. So that is increasing complexity. So very highly complex. So that is also increasing both complexity in hardware and also software. In terms of hardware, how do we connect them? First thing, how do we integrate them with the existing electronic control units? So then how do we process the data? So data processing comes in software. Again, this software aspect is also becoming complex. There, this AutoSAR comes into picture. So I'll just give a preamble. Say I'll quote an example for say before we take up the AutoSAR. Say like any modern cars, as we mentioned, say will have 70 to 100 electronic control units running on its own, say embedded system software. So, but here is a problem. Say, for example, different suppliers build different ECUs. See, everybody cannot build the electronic control units for almost everything. At the end, I'll just show you the vendors also. See, if you consider each segment, there are say if I consider each segment here, say starting from powertrain system, chassis and safety system, body electronics, there are different companies who work on different segment of the vehicle. So they manage the electronic control units. So there lies the problem. So the electronic control unit responsible for infotainment is different. The electronic control unit responsible for so safety purpose are different. The electronic control unit responsible for navigation is different. So this again, they are supplied by different suppliers. So in that case, each uses its own programming style. So the earlier there was nothing like common programming style until AutoSAR comes into picture. So each one of them uses its own programming style, compilers, and of course operating systems. So integrating them in one single car, because I said there were 6 different classes. The electronic control unit responsible for each class were manufactured by different suppliers. Again, the programming style, I mean, I am speaking with respect to software architecture. The programming style, compilers, operating systems responsible for each of them were different. So in that case, integrating them in a one common place is very difficult. So in that case, so I can again, that integration becomes a problem. So you can take a simple example of WhatsApp itself. So imagine like every phone company, so like Vivo, Oppo, they are from same, say, I say Samsung, Samsung, iPhone. So they have their own WhatsApp. Say like every phone company make the app for their own phones. Say like WhatsApp for my cell phone is different, WhatsApp for your cell phone is different. So in that case, integrating, say, exchanging information between them will be obviously difficult. So same way, this applies to the automotive industry also. So same problem was faced until the AutoSAR was introduced. So say like I said, no, different ECUs were manufactured by different suppliers. In that case, message exchange, communicating between them. So that was difficult. So in that case, they devised AutoSAR. So AutoSAR stands for Automotive Open System Architecture. Again, it is worldwide. Say again, it is developed by, say, the giants, leading companies like BMW, Bosch, Ford, Toyota, etc. I'll show you what are they. So again, it is like standardized software architecture and development partnership created by these companies. So the main basic goal of AutoSAR was like, say, to make the automotive software architecture, to make them standardized across the all standard manufacturers. So to make automotive software standardized across the manufacturers. So second is like reusable. Say once the some piece of code is written for a particular application for a particular ECU, that should be reusable. Again, it should not be supplier dependent. So second, next is scalable. So once some say software is defined for a small electronic control unit, say for example you have a rain sensor, automatically wipers have to be turned on. So software there should be scalability. Same if you consider higher order, say like adaptive cruise control, that requires multiple electronic control units to communicate each other. So the standard architecture, software architecture, which is defined under AutoSAR, should be applicable for all the three. So basically, so AutoSAR is automotive open software architecture, which is developed by a set of standard companies. So their main goal is to make the software architecture standard, reusable, and scalable. So of course, they say they come with 2 flavors: AutoSAR for classic platform, which is for one segment of automotive systems like powertrain, chassis, body, and interior electronics. So then adaptive platform, this is for again most of the cases IoT and automated driving, say like comes under ADAS. So I said like the core partners, say which are like BMW, Bosch, Continental, Mercedes-Benz, Ford, General Motors, Toyota, Volkswagen. So they standardize the software architecture for ECU. So secondly, so primarily, so we learned what are automotive systems. Second, what is the requirement for standard software architecture across the manufacturers. So AutoSAR took care of that. So I have a small video. So this is from Tata Elxsi. So just read out. So video was visible, right? Shall I? Okay, or shall I enlarge?
Yes, sir. Yes.
Okay, thank you. Say like say this the Tata Alexi also added to say like AutoSAR. Say they have their own software, say application software. So again, the AutoSAR comes in again three flavors: classic, adaptive, and non-AutoSAR. So that for different segments, as I mentioned in the previous slide, for say so for chassis, body, interior, so that is like classic. Adaptive is for infotainment and further navigation segment. So basically, say like I'll move to the first slide. So AutoSAR framework, say or AutoSAR architecture, say again the segment is like this AutoSAR overview. So it can be summarized into only three parts. So say like three basic stages. So AutoSAR say divides the software into three basic layers. One is like application layer. Second is like RTE, runtime runtime environment. Third is like basic software. So the application layer is like where your vehicle functions are implemented. Say like your anti-lock braking system, so airbag monitoring system. So all others, say like they are like application layer is like where your vehicle functions are implemented. So actual vehicle functions are implemented. Second, if you consider, you can observe here, SWC means software component. So component description is say virtual functional bus is being connected. So this is like more or less elaborated version. So the first layer is application. Second is like RTE. It acts as middleware. So it like it ensures this RTE say ensures like the application can talk to underlying hardware without knowing the exact details. So this is like middleware. So the last primary layer is like basic software, which is standardized across devices, across electronic control unit, and across suppliers. So you can also quote an example for this, like for AutoSAR architecture. So this is like Android OS on your phone. Say like app developers don't need to know what hardware details are there in your phone. They can just install and it can be performed for a specific task. But AutoSAR makes similarly the AutoSAR makes the automotive app development more modular and independent of the suppliers. So basically, the AutoSAR is for standardized software architecture. So to develop the apps, automotive apps, which are standardized across the manufacturers, reusable, write the reusable code, and then scalable for different applications. So this is the overall overview of AutoSAR. Of course, since there are more segments, I'll move quickly because I have to cover the safety. So then next segment is like CAN, last one is like autonomous vehicles. So I'll move quickly. So I mentioned the ISO says ISO standard 262. which is for functional safety. What is safety? Actually, freedom from those conditions that can cause death, injury, occupational illness, damage. So this is like, say, the driver, even the passenger should be, given with safer drive. So again, the system should be reliable. The ability of the system and even the components in the system required to function under worst conditions. So a safe system is reliable. So what is functional safety? Again, it is defined in ISO 26261, absence of unreasonable risk due to hazards, so created by malfunctioning behavior of EIE systems. And of course, road vehicles, say this standard is published in November 2011. So the characteristics of this standard is, so the compilation of best practices for safety related system. In this standard, many development techniques are related to safer systems and safety levels are being mentioned. Say reliability of the hardware is calculated from failure rate of each component. So basically, this standard defines how safer your automotive vehicle with respect to, say again, even the software, say how it provides safety. So the software that is developed in process, so must satisfy all the requirements even under worst conditions. So the standards that are related to safety, functional safety, are ISO 26261 and 2 are there. So I'll go to next segment. So I just quoted the importance of CAN. So to just recall, say the importance of CAN. So if different ECUs are, say they work in isolation, so in that case we cannot say, so we cannot achieve a common application, or we cannot achieve a smoother drive. Say I just quoted the example of adaptive cruise control, so in which multiple electronic control units are involved, so they have to communicate with each other. So basically, so your CAN works as a nervous system for your CAN, allowing your electronic control units to exchange information in real time with lesser delay. So basically, you will have a CAN bus running throughout. So it is, say basically your CAN is like message based protocol, so which enables the communication. It was basically designed, devised in 1986 by Bosch. So the again, earlier to this, I think pre-CAN, I'll show you here. Before CAN, so if we consider the point-to-point wiring system in different electronic control unit, so this is how complex it was, the wiring and even the wire weight. So even the communication between these electronic control unit were very complex. But after CAN, say being proposed, see you can the message being broadcasted. Basically, it is a asynchronous communication protocol, and of course half duplex. So it is like every message in a particular frame format being communicated to each and every node which is being connected to CAN bus. So and of course it will have low latency and highly reliable. So pre-CAN, this was the wiring system, and after CAN being proposed, so the exchange of information was smoother. So let us consider the basic features of CAN. It is a serial bus protocol proposed in 1986, and it is optimized for sending small amounts of data between multiple nodes. Of course, there are very higher versions of CAN can achieve higher data rates, basically from 1 Mbps to 20 Mbps. And of course, the ISO standard related to CANs is like 11898, ISO 11898. So this is for describe the CAN for data link layer 118981. For non for physical layer, it is 118982. So it defines fault tolerant system. So the data link layer is for reliability and safety, safer message exchange between different nodes. So these are the features of CAN. So CAN is a multi-master message-based protocol, basically used for in-vehicular communication. It supports a data rate up to 1 Mbps in classical CAN, up to 5 to 8. Of course, CAN flexible data rate, it is used in ADAS system. If you consider recent version of CAN, it is CAN XL. So it gives the data rate up to 20 Mbps. So the messages are identified with unique identifier. Again, the identifier length is different for different types of messages. So it varies from 11 to 19 bits. So arbitration is based on priority. So lower the identifier, again higher is the priority, again message priority. So CAN uses not return to zero encoding format, NRZ format. So with bit stuffing for reliable transmission and communication. So the maximum payload is 8 bits in classical CAN and 8 bytes in classical CAN and 64 bytes in CAN FD, flexible data rate. Of course, it will have CRC for error detection, and even error correction is possible in recent versions, and can support broadcast communication, allowing multiple electronic control unit to share their information simultaneously. So CAN is basically the nervous system of your vehicle, automotive vehicle, which enables message communication between different nodes that are being connected to CAN bus. So high speed, of course, the standard is ISO, as I mentioned. So low speed, fault tolerant CAN, even single wire CAN specification are there for a lower data rates. So for shorter span, and it is designed for vehicles. So CAN is not only used in only automotive vehicle, it is used in medical applications. It is used in industrial automation applications and many other places. So CAN FD, I think various versions of CAN is being defined here. Say you can say like high speed CAN, ISO 118982. It supports up to the data rate of 1 Mbps, which is commonly used in ABS system, engine control modules, fuel injection, etc. So you have a low speed CAN, fault tolerant CAN. So it is 118983, supports up to 125 kbps. So frequently used in say smaller applications. So single wire CAN, it is designed for say lower vehicles. Of course, the higher versions of CAN, which will have the error detection and error correction say facility, is CAN FD. So CAN flexible data rate. So at the lower side, it will have means higher side, it will have 5 Mbps. So it ranges from 1 Mbps to 5 Mbps basically. So the data byte means the length of the data can range from 8 bytes to 64 bytes. So again, with possible error detection and correction. So it uses CRC. Of course, this is like CAN main benefits. Of course, you can say like advantages of CAN are many. Say like simple to low cost. So you can say like as I mentioned in the previous slide, wiring and weight reduction. Basically, say instead of having complex point-to-point wiring system, as I mentioned in the left-hand side diagram, so you can go for CAN system. So it is CAN system which migrates electronic control unit communication from analog hardwired signal to single bus. So this is what the basic advantage. Of course, it is fully centralized. So say it enables you to about central diagnostic, data logging and configuration. It is extremely robust. Of course, say efficient. So reduce this vehicle weight. Say more or less, this is very important. And deployment is very easy since each and all the nodes which come are connected to a CAN bus which is running throughout the vehicle. Of course, it is basically it is resistant to EMI, electromagnetic interference. This makes CAN ideal for critical application vehicles. So it is basically resistant to EMI. So of course, CAN main advantages are summarized here: simple and low cost, fully centralized system, extremely robust and efficient. So how does CAN work? So of course, basically there are only 2 layers. Of course, we all know 7 layers of OSI model, starting with physical layer till application layer. So CAN sublayers are basically, you can divide them into physical layer and data link layer, which in turn can be divided into two. One is MAC layer and logical LLC, logical link control. So this is defined in ISO 118981, 118982. So how does CAN works basically? So the devices on a CAN bus are basically, we call them as nodes. Each node consists of, I think I have a block diagram. No, I'll stick on to this. Each node consists of a CPU, so CAN controller and transceiver, which adapts the signal levels of both sending end and receiving end by the node. All nodes can send the data and receive the data, but not at the same site. That is same time. That is why I mentioned it is asynchronous. So then it is half duplex. So basically, CAN is half duplex and asynchronous. Nodes cannot send the data directly to each other. Instead, they can send the data on the network where it is available to any of the node. So again, basically it is addressed through the message. Again, it is, since it is message based protocol, basically it is addressed through the bytes. The CAN protocol, of course, it is lossless, employing a bitwise arbitration methodology. So all basically we can consider all nodes on the network. I think the diagram is missing. So only frame format is being included here. Sorry for that. So all nodes on the network are synchronized so that they all sample the data simultaneously. So how the again, since it is synchronous, it is there is nothing like clock. So CAN is basically asynchronous bus. So all basically the frames. I'll consider the frames now. So the frames in CAN, there are four data frames, four types of frames which CAN uses for communication, for message passing. One is like data frames. So it is the use for transmission of data to one or many nodes. So second class is like remote frames. So it is like ask the data from other nodes, say like reception. So third classes of frames are like error frames. This is for reporting error or error detection. So last one is overload frames to report the overload condition. So the basic frame structure of CAN is displayed here. So again, say it consists of startup frame, 11-bit identifier. So then RTR, say standard CAN identifier, received bit, whether you are transmitting or receiving, data field length. So this data, say it can vary depending on again. So what standard of CAN you are using? So for basic CAN, it is 8 bytes. So when you go for CAN FD, it can go up till 64 bits, 64 bytes. Again, it will have a CRC check along with the acknowledgement. So of course, frame size extended CAN data message. So this is how, say, wherein you'll have basically 29-bit identifier along with 11-bit identifier. You'll have a 18-bit, so which is extended CAN. So you can say like say this 11-bit identifier sets the message priority. So the MSB basically say the MSB, whether it is 0 or 1, depending on that the priority is being set. So lower values means higher priority. That is what how the priority is being set. So again, this RTR, say like remote frame request. So it is for remote transmission request. So this is the standard CAN format, say more or less across all applications. Of course, the history, say this is the timeline. So 1986 they had proposed. So the recent version of the CAN is CAN XL. So that support still higher data rates. It can go till 20 Mbps or higher. So of course, the moderate for moderate ECUs, it ranges from 1 Mbps to 5 Mbps. And say wherever the autonomous vehicles came into picture, the data rates can swing up till 20 Mbps. So applications, as I mentioned, it is not only used in automotive industry, in all other say like wherever there are multiple electronic systems being deployed inside the vehicle or wherever safety is required, they are using it. So as I mentioned here, in the medical equipment, say like imaging devices, MRI, CT, ultrasound communication. So in patient monitoring systems, even in agricultures wherein heavy duty vehicles are being deployed, and even in aviation vehicles and aerospace vehicles, UAVs, unmanned air vehicles, and networks of UAVs, they use CAN bus. And of course, basically in automotive industry, they use for ECU, different ECU communications. So they use CAN bus for communications or message passing. So I would like you to
network, or CAN,
listen
is
to
a
the
powerful
summary of CAN.
communication protocol used in various fields like automotive and industrial systems for real-time data exchange. Its multi-master and broadcast communication allows multiple devices to send and receive messages efficiently. With features like priority-based arbitration and robust error detection, CAN ensures reliable communication in critical systems. The CAN frame format consists of several important elements, including the start of message, identifier, control field, and data segments. There are various types of frames in CAN, including data frames for sending information and error frames for reporting issues. CAN is widely used in diverse applications, from automotive communication and diagnostics to enhancing industrial robotics and patient monitoring in medical fields. It even extends to aerospace for avionics and healthcare for patient monitoring, illustrating its versatility across multiple industries. In conclusion, the CAN protocol stands out for its robustness, making it an essential choice for real-time data exchange across various applications.
So this is a simple summary of controller area network. So more or less it is used for communication between electronic control units that are being deployed across the vehicles. So, and of course it will have a standard frame format. Depending on what application we are using, the format, there are only two. Of course, the higher versions will have higher bytes of data. So it ranges from 8 bytes to 64 bytes basically. So further moving on with last segment of my presentation, I said like the say different levels of automation, the automotive embedded systems inside the vehicle. So they changed over the era. So what were the embedded systems in the earlier days of safety, and what are now and what are being proposed? So again, these are like 2018 slides. So from Bosch only, Bosch, and majorly the content is from Bosch and Continental, say there for educational purposes. So you can segment the say we say basically the radars deployed inside the autonomous vehicles or vehicles into different 5 timelines. So 1950 to 2000, it is for basic safety and convenience. You can say like seat belts and anti-lock brakes were used deployed until this period. When you move segment to the next decade, 2000 to 2010, so advanced safety features like electronic stability control, blind spot detection, wherein they started using like cameras and some radars for collision avoidance and collision warning. So next, not avoidance, warning systems. So next, if you consider 2010 to 2016, this is where they started, say, manufacturing wave, looking into wave radars. So most of them gave, and of course, computer vision systems are being realized on FPGAs. So there multiple advanced driver assistance features came into existence, like rear view, automatic emergency braking, pedestrian emergency braking, rear collision avoidance system, rear cross traffic alert, lane change assist. All those things came into picture. They sell like 2016 to 25 partially automated vehicles, and of course you see in multiple say in different parts of the world some use cases of say these things fully automated vehicles. At the end, I think I'll show you one case study from India only. I think Zpod was the first autonomous vehicle they deployed to cruise between two fixed locations. Now even IIT Hyderabad, they have one startup which has developed autonomous vehicles to navigate or to carry passengers like faculties and students across different parts of the campus. So these are like 5 eras of safety. As we move from say one level, they say this is level 1. To level 5, the number of sensors that are being deployed into the vehicles are more. The number of automotive embedded systems in the car, our car or vehicle got increased. The complexity in the network between electronic control unit got increased. And of course, the safety also, the number of vehicles on the road also got increased. So to add on the safety, so the number of sensors, number of automotive embedded systems that are being deployed into the vehicle got increased. And of course, the road to the full automation is like this. So earlier driver assistance, like you drive, you monitor. So that we say, like say only warning systems were there, say, to display what is the say condition. So then conditional automation, the system drives. So whenever you give an option, it will take over upon request. So whenever the say road is like more or less say straight. So at the higher end automation, when engaged system drives, you can also ride. So fully automated vehicle. So when engaged, it will drive in any condition, and of course, it allows also you to drive. So this is 5 levels of automation. I mentioned the complexity. You just observe the number of radars. I have particularly taken only radars because I work on radars, specifically mmWave radars. So you can observe the number of radars, say in each level. So if I consider level 1 for driver assistance, you can observe the object detection radars. SRR stands for short range radar, which can go till 50 meters max. So the applications are like blind spot detection and lane change assist. So these are also automotive embedded systems. Of course, slides are taken from ST Microelectronics. So there were 2 short range radars in this level. If you consider level 2, wherein partial automation, you have a collision avoidance, which require long range radar. It will go up to 200 meter. Of course, ideally it works 100 to 150 meter. So the applications are again range, adaptive cruise control, automatic emergency braking. So here you observe there were 3 radars. So now consider the next level, 2018. So there were like high resolution target separation are required. Here they started deploying cameras also. But look at the number of radars, 4 short range radars at each end. So this gives the visibility around the vehicle. And of course, it will have a forward collision avoidance system. So then look at the level 4. Apart from these 4, you will have 2 short range radars. So this allows you 3-dimensional detection. So lastly, you observe, they say greater than 2018. So fully automated vehicle, just observe 360-degree object recognition. How many short range radars? Ultra short range, most of the cases, it is for parking assistance. So say it will have nearly 8 radar, more than 8 radars actually, to be specific. So it will give you clear 360-degree vision, even for the driver, for the vehicle to take say decision. See how complex this system should be. So each electronic control unit associated with each of the radars has to send the data, has to process the data, has to take the decision within milliseconds of delay. That is how the complexity will be in a fully automated vehicle. They say automotive radars versus automation level. So whenever they started for fully automated level 5 fully automation, so the number of radars also increased, number of sensors deployed in the car increased, and of course all the say acronyms that I have mentioned in the downside, they are like embedded systems only, automotive embedded system. They'll have particularly designed for one particular application. Say for example, forward collision avoidance, it will have the task of detecting any pedestrian or forward moving vehicle at the opposite side and calculate the distance at which the object is present. Once the object is present within the critical distance, it has to take over and apply braking. This is forward collision warning. Even avoidance system are also there in Tata trucks. Case study, I think in YouTube, if you search, both in Tata Harrier and Tata trucks, both forward collision, rear collision, even blind spot detections are being installed. So you can observe that videos I have not got. So basically your driver assistance system will have 3 parts. One is like sensors, second is like processing unit, your electronic control unit, and output you can segment into three. So one is like you inform the driver or passenger, you warn the driver whenever a criticality is being met, and of course, if it is fully automated vehicle, you intervene. This electronic control unit or multiple electronic control unit takes over and apply brake or any other decision is possible. So basically, ADAS is like it will have three segments. One is like sensors, electronic control unit. Output can be three: inform, warn, or intervene. So this is how now recent versions of car, the advanced driver assistance some features look like. See, I'll start from longer side. Adaptive cruise control, actually it should monitor till 150 meter. Automatic braking, pedestrian detection, collision avoidance, it should go up to 100 meter. Traffic sign detection, this up to 50 meter or 50 to 100. So crash traffic alert 50 meter, parking assistance up till 20 meter. So for most of the long range, they use lidars. So for most of the short range, they use radars, millimeter wave radars, and of course they use cameras for clear vision and classification. See, cameras are being deployed for surround view. They assist the driver for say easy cruising between say one place to other place. See, observe the number of sensors and observe the view either the driver or vehicle is getting. And of course, imagine the amount of data that is being exchanged between the sensors and electronic control unit. So this is how formally we can say most of the cases we can more or less we can say the summarized version of the block diagram for a particular embedded application can be like this. Either it can read the data from camera, radar, laser, say like lidar, ultrasonic sensor, say GPS sensor, vehicle to X telemetry, take these inputs from the sensor, make sensor processing, means maybe we can say pre-processing, removal of noise, converting physical to electrical equivalent, then giving our A to D converters to be specific, give it to digital signal, digital processing and fusion, means some application may require data from multiple sensors. So in that case, combine it and then give it to the output, means each of these, say like input processing, data processing, fusion. So it is controlled by multiple electronic control units, means each electronic control unit will have a to D converter, D to A converter, sensors being integrated, microcontrollers in some cases, and of course the display. So output can be, of course, throttle, braking, throttle, steering, and driver alert or intervention. So basically this say inform, warn, or intervene. So the last part is like connected vehicle. I'll not, I think, so I don't know what, how much time I have left with. So, so any organizers, like how much time I have. So how much time I'm left with?
Sir, you have till 8 o'clock, sir. Your session is till 8 o'clock. You can continue, sir.
Okay, okay. Say last part, say like I just took the radars for ADAS features. So now the last part of it is like the more or less the extension, vehicle to X communication. They say vehicle to infrastructure communication. Under massive MIMO or say if it is being deployed 6G or 5G, they say every infrastructure, even the signboards, they'll have wireless transceivers. They exchange information with all the vehicles that are being connected. So if I say connected vehicle, so a connected or to be specific connected car, so it will have the wireless connectivity between the surrounding. So the surrounding may be other vehicles which are moving around, or other vehicles which are moving around, or the infrastructure, say like traffic signboards, so traffic signals, or cameras that are integrated with the camera, with the traffic signals. So again, basically the exchange of information, there should be safety. First thing is safety. Second is like permission should be there. They should communicate using again particular frame format. So first connected car, of course, it was developed by General Motors in 1996. They sell like say the connected cars. So in different perfect perspective, they look. One is for vehicle to vehicle communication or vehicle to X communication, and second is connected. It is digitally connected. So earlier it was before 2010 it was only infotainment. So in recent after 2020 it is like self-driving cars, more or less V2X communication. So basically connected cars are say like this. So it is for starting with virtual means say diagnosing the vehicle, accident detection, stolen say vehicle tracking. So these features are mostly built in say in recent coming cars. Say driving behavior means whether it's rash or whether it is driving appropriately according to the road condition. Again, vehicle evaluation means vehicle diagnostic, where vehicle is moving with what speed. Again, it is connected to the again centralized system or other wireless transceiver. So future car connectivity so should integrate almost everything. And of course, this is like more or less the features. Say like noise level adjustment, self semi-autonomous, say Bluetooth connectivity, GPS connectivity, in-vehicle wellness, so then smarter keys. So all these features, if they are integrated into the vehicle environment, we say they are connected cars. Of course, I mentioned vehicle to X communication. It can be vehicle to vehicle communication. Say if our car has say wireless transceiver, it can exchange the information with other connected vehicles. So that we can quote it as vehicle to vehicle communication. So this is like vehicle to infrastructure. As I mentioned, say traffic signals can have wireless transceivers. In that case, if permitted, it can exchange the information. So vehicle to motorcycle or vehicle to two-wheeler, vehicle to object, vehicle to pedestrian. Basically, they say X vehicle to anything communication, anything which is being wirelessly transmit and receive the information. So this is like future. So of course, they have defined a standard, say IEEE 802.11 to support wave DSRC. So this is again, there are again classes, say the frequency at which they operate, they quote like sub 6 gigahertz, so 5.8 to 5.9 gigahertz, basic OFDM. And again, there are, say, safety aspects with respect to vehicle to X communication. So that it should, again, the communication protocol should take care. So this is like vehicle to X communication. So lastly, say like any autonomous vehicle, they say in Indian road scenarios, it is not possible to have an autonomous vehicle, fully automated vehicle. But for specific application like industrial automation, so in campus mobility, or within two particular location, say given the path is fixed, in that case we can say devise or design autonomous vehicle. So one case study is here, can have.
As part of efforts to build smart mobility solutions for Indian conditions, a team from IIT Hyderabad has developed a software for driverless buses to navigate through the institute's campus. The AI-based technology has been created by the Technology Innovation Hub on Autonomous Navigation, or TIHAN. This is TIHAN's Autonomous Campus Shuttle. Welcome on board, and is being used to transport students and faculty in vehicles within the campus. Autonomous Campus Shuttle.
So this is like I got this video recently from YouTube. I just downloaded only part of it, so you can anyhow. I'll share the slides. You can look at this video complete. So it is used to carry say students and faculty members across the campus. So that is possible. Most of the cases, the vehicle density and even the pedestrian density, they'll have their own lanes. Even the vehicle density is less. So in that conditions, we can design autonomous vehicles, provided the sensors, radars, and then cameras being integrated for the same purpose. So I said like different parts of electronic control means different parts of the vehicle. There are different suppliers, there are different vendors, and there are different competitors. So you can say like autonomous solutions, these are the competitors. So regarding signal processing aspects, so these are like contenders. Regarding sensor development, so these are the suppliers. And regarding connectivity, say like communication protocols, so navigation, so these are the companies who work. Again, mapping, these are the companies. So security and safety features, so these are the companies. You can observe like wherever the hardware development is there, wherever sensor development, wherever safety features are there, Bosch is there. And most of the software development and sensor development, Continental is there. So one observation you can say. And of course, camera based solutions, there are many companies who are working. One of the prime is like Toshiba and Nvidia. Say lastly, you have so many development tools. And of course, Texas Instruments, most of the millimeter wave radars, so that we have worked on is from Texas Instruments. And this software package which is necessary for processing the data and carrying out the detections and tracking, the development tool is given by them only. It is their own. So like millimeter wave studio from TI. And of course, it is compatible with MATLAB. Most of the software defined tools are compatible with MATLAB. Another thing is the communication protocol. Most of the cases, it is vector canalizer. So canalizer, it is the tool to extract the information or read the CAN packets which are being exchanged between different electronic control units. So these are, say, this is how say different companies, they came together, say in an automotive industry. So they work in different segments. So you can say like level of integration. So I said like dashboard. So I'll show you the dashboard at the end. So each of them, say like even I don't know. So many of them. So here say like fog light control, power steering, fog light rear, say washer fluid low, brake pad warning, cruise control, so rain and light sensor, winter mode, so then frost warning. So most of the icons here, almost everything, they indicate embedded system. They are associated with an electronic control unit. Of course, so the complexity runs over. So I have come to the end of my presentation. I tried, say, earlier, I think in the earlier slide, I was in a hurry. Say, I just wanted to just introduce the various segments of automotive embedded systems. So I started off with the basic definition of automotive embedded systems. So need for automotive embedded systems. The flow was like, so I'll go to the first slide. So this is like CAN. So I tried covering these four aspects basically. So I tried covering. So what are automotive embedded systems? What are the general features of automotive embedded systems? Classification of automotive embedded systems. So what is the basic core of an automotive embedded systems like electronic control unit? Features of electronic control unit. So the classification. So then how to say we considered both hardware aspect and software like so why do we need a common software architecture? So then very basic features of AutoSAR. So I think in further days they'll get into the details of AutoSAR probably. So then basic message passing, say message exchange communication protocol like CAN. So then advanced versions of automotive embedded systems in recent applications like autonomous vehicles and connected vehicles. So I hope like I covered all the four. So most of the slides are like general. So I have taken from Robert Bosch training, which I had attended long back. So some slides are say like the contents might have updated. So and of course you can get the autonomous vehicles related to CAN. You can go to the Bosch website. Say their learning website is there, so there you can get the details of CAN. And related to autonomous and connected vehicles, I think Continental is the best place. So I'll conclude here. Like I summarized all the four aspects of automotive embedded systems like AES, AUTOSAR, CAN, and connected vehicles. So thank you. Thanks for listening.
Just 2 minutes, sir. Just 2 minutes. Any participants, anybody is having any doubt, you can ask the today's resource person, Dr. Purushottam, sir. Any doubt from any of the participants, you can unmute and you can ask the questions, please. Anybody is interested, please?
So even if it is like, say, to be frank, we work in specifically radars, say millimeter wave radars. So basically detection, tracking, and safety. Again, related to any other content in slide, you can post a query.
Any doubts? Any doubts? Even you can unmute and or you can send a message also. If you have a, yeah.
Good evening, sir.
Good evening.
Sir, for autonomous navigation,
Sir.
do we use any particular type of OS, sir?
For autonomous navigation?
Yes.
Say again, particular OS, say it is again yet to standardize. As per my knowledge is concerned, they use again AUTOSAR only. It is depending on what sensors you are using. So that Tihan I have shown, no sir, IIT Hyderabad. So they just integrated various, starting with LIDAR and other sensors. Say I think connected map. So for platooning, they've used. So related to software, I don't have much idea. Specifically, I don't know whether specifically they have used some particular software. I don't have the idea. Basically, it is sensor processing and navigation, and so aided with navigation. So I don't think any particular software is being used apart from AUTOSAR.
No, particular any OS.
OS.
And recently I heard QNX RTOS is one of the most upcoming OS which is taking over AUTOSAR.
Oh, maybe, sir. Maybe. So, as I said,
I think in your slides also you have mentioned about QNX, sir.
QNX, I think V2X. I think.
No, QNX is there at your different brands. What you have shown, that QNX is also there.
Yes, sir. Yes.
Okay. Thank you, sir.
Thank you.
Hello.
Yes, ma'am.
Any questions, sir, from any of the participants? Any other questions? Okay. Okay. Thank you so much, sir. I really, behalf of Sahe family, my heartfelt thanks to Dr. Purushottam TL, sir, Assistant Professor SIT. Really, it's a wonderful session where you have briefed out regarding the basics of an automotive system and the CAN basics. Really, it's a wonderful session, sir. Thank you so much, sir. Thank you so much.
Ma'am. Hope I have not bored.
No, sir. No, sir. It's
online.
really, no, sir. It's very
I hope
interesting.
like it was not a boring since I took almost 1.5 hours. Thank you.
Thank you, sir. Thank you so much,
sir. I thank Komla Madam and SSIT for giving me an opportunity to share whatever I had. So thank you very much.
Thank you, sir.
Thanks
Thank you.
for listening. Thank you.
Thank you, sir. Pleasure to have you. Thank you.
Thank
Now
you.
I request Dr. Vidya KV to give the introduction about our regarding the second session speaker, Dr. Sumana Achar, Associate Professor, AGM Rural College of Engineering and Technology, Hubli. Vidya ma'am?
Yes, ma'am.
Yeah, please do
Good
give
evening
a...
to everyone. Good evening to everyone present here. It gives me immense pleasure to introduce today's distinguished resource person, Dr. Sumana Achar. Dr. Sumana Achar is an associate professor in the Department of E&C at AGM Rural College of Engineering and Technology, Varur, Hubli. Madam holds a PhD in Electrical and Electronics Engineering Sciences from VTU Belagavi. Her research is related to router architecture on FPGA. Madam completed her MTech in VLSI Design and Embedded System in 2019. Sorry, 2009. And her BE in Electronics and Communication Engineering in 2002, both from VTU Belagavi. Madam has over 21 years of academic and industrial experience. She has worked as software engineer in Mata Electronics and Inflow Global India Limited, where Madam has worked on areas of SAP. She has enriched her knowledge in FPGA design at previous company Indian Research Network, Bengaluru. Madam has been actively involved in teaching, mentoring, and research in the VTU affiliated institutions under core areas of interest include VLSI design, network on chips, computer networks, embedded systems, and IoT. Madam has guided numerous student projects and continues to contribute to research through scholarly publication in national and international journals and conferences to stay updated of advancements in her field. To have you with us, ma'am, I warmly welcome you on behalf of Saheb family, and the session is now yours, ma'am. Over to you, ma'am.
Thank you, madam. I'm
Thank
very
you.
much pleased to be one of the resource person for this ATAL FDP. My topic, which was allotted to me, was RTOS architecture and task scheduling. So prior we move to the real-time operating system, we need to know what actually is the operating system. So operating system, it is a piece of software that manages all the resources of computing devices. Now, it runs on the computer or microcontroller that accomplishes several important functions. First, it is in charge of scheduling background tasks and user applications. In most of the operating systems, dozens of tasks are executing at the same time. And you probably have several applications open in your phone right now on your computer. The operating systems figures out how actually it has to be slide out all those multiple applications which you're watching right now. It has to slice the time and then allow those tasks to process. So everything appears to be happening concurrently. The second thing is it manages number of virtual resources like file libraries. Where I can just say that the libraries and the folders allow applications and processors to access them when needed. The third thing is device driver. They can manage or provide device driver for the system that we use. These drivers allow the system to read and write from an external disk. It can respond to the keyboard and mouse input or draw graphics on your monitor. You probably have come across the general purpose operating systems like Windows, Mac OS, Linux, and right now for the mobile phones like iOS, Androids. They fall under the category of general purpose operating system. Most general purpose operating systems are designed with human interaction. So they give prioritization to the human interaction. So the scheduler is designed to prioritize such tasks that they mean something where the deadline is not much important. So wherever we expect the deadline, That is, if the event is very critical and it has to be executed within certain time constraint, then there comes the real-time operating system. So the scheduler in this case, it has to prioritize certain tasks and allot certain timing constraint to it. In case of general purpose operating system, deadlines can be missed. But in real-time operating system, we are not able to, like operating system should not miss the deadlines because it may cause certain issues in the life saving steps. So the scheduler, whatever has been accepted, it is like it should be deterministic. The scheduler in case of general purpose operating system is non-deterministic, but in case of real-time operating system, it is deterministic. So I have here shown that the task scheduling, resource management, and the device drivers, whatever folders are, whatever task management systems are there, all these are available in general purpose operating system also, but those general purpose operating system, they are not deterministic. So here I have shown ESP32, which has a real-time operating system in it. We can load the free RTOS in it and then try to use it as a real-time operating system where the certain time constraints we can apply on the ESP232. Now, general structure of operating system is it has hardware as an underlying bottom level board. It can be motherboard with a processor, and on top of that, it is the operating system. Then over that, we have the application software, like I have just shown certain examples of it, MS Office. And later at the final level, it is user. So the operating system here, it is acting as an abstract level. It is trying to bridge between the application software and the hardware. That is what actually is an embedded system. So operating system is just a software layer. It is abstraction layer between the hardware and the application software. It has direct access to the hardware, but the application software has to communicate with the operating system and then access the hardware. So what actually operating system is doing is it is trying to hide the complexities that occurs while the application software accesses the hardware. So application software, if it requests for certain data, then the operating system, what it does, it simply manages all the complexities like time management, resource management, all these managements related to the task that will be managed by operating system, and then it will simply access the hardware. So it offers multitasking and resource management also. Examples of operating systems are Windows, Linux, Mac OS, Android, iOS, embedded OS, and all. So what actually is a real-time operating system? So RTOS is an operating system which is designed to manage hardware resources, and it is intended to serve real-time application that processes data within the strict timing requirements. There should not be any buffer delays, and it has high degree of reliability. It means that RTOS is having two components, where real time and it is also an operating system. When we say real time, it has to meet the deadline. It has certain timing constraint, and operating system is the general purpose operating system. So RTOS is also an operating system which has imposed certain deadlines to it, to the task which it executes. So it has to have high degree of reliability. There should not be any delays because any catastrophe may occur. And why RTOS is needed when general purpose OS exists? RTOS actually is deterministic, I said. It is a real-time response. As I said, it has certain time constraint. Within 10 millisecond, if a task has to execute, then it has to execute within 10 milliseconds. We cannot call the faster OS as RTOS, but we can call the RTOS as deterministic only if it meets the deadline. And also, RTOS has to be efficient in managing the task. It should have certain low latency, and it should be highly reliable, as the definition says. And it has to have resource optimization. It should be able to manage the resources that are required for the application softwares. And safety and stability also should be the priority for the real-time operating system. Um, the the real-time operating system, it should, I can just categorize a task like this. I should have a real-time system as one of the major component of real-time operating system. Like spontaneously, it has to respond to external system in timely fashion. It is characterized to meet the deadline. Real-time performance does not meet the faster performance. Like as I said, I cannot call a particular processor as if it is very fast, then it is a real-time operating system based processor. That is like if it is taking its own execution time, it should meet certain deadlines. If it has to execute the task within certain time constraint, only then we can call the operating system as real-time operating system. Uh, the types of real-time systems are hard real-time system, where it has to meet the deadline all the time, even under certain worst case load also. If missing a deadline may cause certain fatal consequences, where it may be like a problem to the life also, human life also. So I can just give an example as airbag system or the pacemaker in the heart. If it is not performing properly, then it may cause certain harm to the human life. The other kind of real-time system is soft real-time system. Missing a deadline does not cause fatal consequence, where we need not worry about. Actually, it has to meet the deadline, but certain period of time it is not able to meet certain deadline. Then that may not be so much important for us, because the quality of the system, quality of the service, whatever it is providing, that may reduce, but it is not causing harm to a human life. In such a case, we call such a system as soft real-time system. So if it is missing a deadline and it is does not causing any fatal consequence, then we call it as a soft real-time system. It may lower the quality of the service also, but it is not catastrophic. Means multimedia devices, or the I can just give an example of broadcasting. If at all we are broadcasting certain videos, and 20 frames per uh, second, if we are transmitting the data, if one of the frame, if it is missing, then it will surely reduce the quality of the video, but it is not harming the transmission. We have received the data, but we can ask the transmitter to send back the data. It is not a problem actually. It is not causing any harm to the life. But in case of hard real-time system, it is a life safety system which has to take care, where the deadline has to be met 100%. And in case of worst case load also, it has to meet the timing constraint. RTOS characteristics for single task or multitask. Now, suppose we have a single task system. Without RTOS, only one task can be executed by the CPU at a time. For critical applications, if we have a lengthy programs that is which is a task that is getting executed in the operating system, then that task may take a long time. It is a forever super loop, I can call it as. It is an infinite loop that is getting executed. Only I have one CPU core which is available, which is executing the task. In such a case, the next task has to keep waiting for the CPU time. If at all if we have certain critical application, in such a case, interrupt service routines, some hardware interrupt has to be initiated and interrupt service routines are to be executed. So in case of single task system, the kernel is totally dependent on execution of the one task, irrespective of the time constraint. Suppose we have multitask system, then here the CPU time has to be scheduled. Like RTOS allows execution of multitask system on single CPU only. And nowadays we have multiple cores also available. The task can be executed in multiple cores also. But suppose I have a single CPU and I want to schedule the task on the single CPU, then the CPU time has to be sliced down. Like RTOS is that system which allows execution of multiple tasks on single CPU. All tasks execute as if they are owning the CPU. Means the CPU is giving like the processor will not come to know, like the user will not come to know that there is certain delay in execution of the task. We feel as if all the multiple tasks are getting executed parallelly. Tasks are scheduled for execution based on the priority and is done by scheduler in the kernel. Here I have taken an example of a super loop. Here I have three tasks that are in a while loop, let us say while one loop. Then entry point is just a setup code that has to be executed, and task 1, task 2, task 3, all these are continuously getting executed in a infinite loop. Suppose we need to interrupt this execution, then we need to have execute the interrupt service routine. There should be a hardware interrupt that need to be initiated. So, and execute the interrupt service routine in case of certain catastrophe. As I said, like we can have multiple core also. Each task can be allowed to each multiple core, each core, and it can be parallelly executed. Suppose we have a single system, task system, then it is very difficult to maintain when the program, maintain the real-time operating system where the program becomes very complex. So because we have a while one loop, which is executing forever, right? So the super loop, it is a super loop where it is not allowing any other task to execute. In such a case, in such a case, in such a case, interrupt service routine need to be executed. So reaction time depends on the complete execution time, where the system is not so simple, and if the system is very complex, in such a case, we can just go for a single task system. Multitask system. Here, you can just see that we have a scheduler. The task is getting selected. So CPU time is distributed among the task. Each task takes ownership of the CPU. You can see that you have the priority also matters to each task. High priority and low priority level wise, the task is getting distributed. The scheduler decides which task has to be executed when. Like the CPU time also is the CPU selection happens based upon the priority. So here the events can be signals or messages from the task, whatever interrupt service routines are there, that is fed to the real-time kernel, and that will communicate with the scheduler, and the scheduler will assign the priority based upon the priority. It will allocate the time slice to each task. Now here scheduler is just a software library. So it is trying to provide the processor or the CPU time to each task. So we can have many number of tasks, but the priority has to be assigned to each task. If the priority is very high, then the time slot is given to the high prioritized task. And of course, the task is been scheduled based upon the resource requirement also. And if suppose we have a task which is executing at shorter time period compared to the next task which takes long time period, in such a case, based on the execution time also, the priority can be changed. And sometimes we may have some hard interrupts. In such a case, where the deadline has to be met, the priority can be given to the task which has more time constraint. So the scheduling in RTOS, it takes place based upon various resources requirement, priorities, execution time, or the time constraints, or how many number of tasks we have. Based on all that, the scheduler, which is a software library, that decides how the CPU time has to be slides down. So what is RTOS architecture? Now, RTOS architecture, it usually comprises of only kernel. Uh, Only one kernel is enough for RTOS. But for more complex embedded systems, an RTOS can be combination of various modules. Like I can have networking protocols, stacks, or some debugging facilities, some device drivers, file systems, or ANSI compliant, some C libraries we can have, or POSIX supports we can have. All this, the other components also come into picture when we talk about the complex embedded system. So typical RTOS architecture, which is a basic architecture. Here we have application layer where the applications may be related to automotive or industries like IoT based solar energy harvesting system or battery management system or anything of of such sort, or it may be related to medical devices. So those inputs that comes from the sensor are handled by the application layer. And in case the at the center, you can see that here you can see that it is a RTOS kernel. Actually, this RTOS kernel, only one RTOS kernel is enough to execute a task, but which can be a interface between a hardware and the application layer. But we require multiple components. As you can see, network security files are needed, and lightweighted file systems are needed, lightweighted network libraries are needed, debugging or tracing, and some security files uh, other than network security. All those are need to be available along with RTOS kernel. So the architecture depends upon what applications we have designed. So any architecture it may be. See, when we say an architecture for any system, then to what applications we have designed that system. So based upon that, the architecture keeps changing. So the basic architecture for an operating system is like I should have a user space, I should have a kernel space, and there should be hardware. Right. Here also we have user space and the application layer, and RTOS kernel is a mandatory heart of the operating system, and also we have hardware also underlying device. So so this RTOS kernel, which is a abstract layer that communicates between the application layer and the hardware. So kernel of usually has like any operating system, when I say it has two space, I said kernel space, user space. So kernel space is actually the core of the operating system. In this space, OS executes and it provides its services to the application layers. And in case of user space, space of the system memory is utilized when the process runs. So therefore, architecture depends totally on the nature of the functionalities. And this kernel, what we say, it is very smallest and central component in the real-time operating system. It provides service to manage memory devices depending on the architecture. Kernel may have some other protection of programs, multitasking, some management softwares it may have. So uh, uh, kernel can execute any programs, a a particular task. But if we want the CPU time to be sliced up, then we need to have multiple scheduling, multiple components like scheduler we require other file systems, other resource management system, everything. So this abstraction layer, it comprises of many main services that are provided by the kernel to the application software. As I said, like um, manage time management system. It has to handle the interrupts. It has to manage the memory and the resources. And of course, IO management is required. And task synchronization and intertask communication has to happen by, of course, it is also called as interprocess communication. So to make this happen, the RTOS requires multiple layers in it, multiple components in it. We have three categories, the three basic categories in RTOS architecture. Like we have monolithic kernel is one of the category in kernel model. So here what it is a monolithic kernel. It is also an operating system, but it acts as the kernel, like it actually runs the it is run in the kernel space only, but it has all file system, device IO management, interprocess communication system, fundamental process management, everything lies in the kernel space. So this design, it is with other architecture, like we have other architecture like microkernels or exokernels. Compared to that, it has all the basic services that are run in the kernel space only. Here, the services, there are like application libraries, application softwares, library softwares, all these run in the user space. Um, the key characteristics, like high performance is provided by the monolithic kernel. That is because very less interprocess communication overhead we see, because the kernel space itself has interprocess communication included in it. So there is absence of overhead that occurs in the kernel space, and a single large process can execute in a single address. So that's what I said. One task can be executed, a lengthy task can be executed in the kernel space. Only one kernel is enough. Only if we want the CPU time to be scheduled, and then we require multiple features that has to be added to the kernel space. So the advantages are like it is very efficient, and efficient system calls can be handled. It can do provide CPU scheduling. It can also function through system calls, the file management, memory management, everything can be done together by the operating system only. The lack of complex interprocess communication, that will speed up the system call actually. And the model, we also see the modularity in the kernel model, where like Linux and BSD system operating systems, if we have dynamically if we have the load dynamically changing, or if at all modules are executable at during runtime only, then these modularities also allows for easy extension of the operating system capabilities. So if we extend the operating system capabilities within the required operating system, then it may require a reboot also. That is a must. but modularity exists. Modularity can be seen in this particular kernel space. So, but the disadvantages are there are some stability issues. If in case of any service fails, then it can lead to entire system failure. If there is lack of isolation between the services, it can compromise system stability, and some bugs or vulnerability in the service, if it exists, it can affect the entire system, because everything is available in the kernel space only. And because the kernel software code, it is nothing but a piece of software, right? So because they are existing in the kernel space, the system is becoming more complex. And as and when the data that we receive from the external sensors, uh, then what happens is more services are getting added to it. So it will make it difficult to uh, maintain the task that has to be executed. It is difficult to execute the files in the kernel space also, and very difficult to debug in case of any faults that occur in the operating system. The second one is microkernel. Here, to overcome the disadvantages what we have seen in monolithic kernel, the kernel space has been reduced. Like all the file systems, process servers, library, time management system, all these which were there in the kernel space in case of monolithic operating system kernel space, it has been moved on to user space. So in case of user space, you can see there you have the software, application software. Along with that, you have the server files also. So it is like we have reduced the lengthy code that need to be executed in the kernel space. So the complexity in the kernel space has been reduced. So this is actually the minimalistic approach which was thought for designing an operating system. Here, all the memory management system, task scheduling, interprocess communication system, resource management, everything is happening outside the kernel space block. So we can say that the disadvantages, whatever we have compared to the fault debugging, it may be handling the large size in a kernel. All this, by the look, we can see that it has overcome in case of microkernel. But the characteristics, key characteristics are like it has a minimal core, that's an advantage, and the stability and fault isolation. Because the fault and see, the fault, if it occurs, then it is handled at the user space only. Because we have a separate server management system, so naturally the kernel space is not hindered. In such a case, the stability and the fault isolation is managed in case of microkernel. And security also, it has been included in the applications, software applications that are available in the microkernel. So examples are Amiga OS and QNX. QNX is a RTOS architecture, which is very efficient in case of embedded system. And disadvantages are slower message passing. Means uh, see, this particular system also can handle the uh, what efficient system calls. But what happens is, in case of the message passing, in the sense, see, we have a server applications which is in a user space directly. What was happening in case of monolithical? all these file system, process server, libraries, not libraries, sorry, interprocess communication system, everything was available in the kernel space. So accessing those file system was not difficult. But here, as we have a separate server block available in the user space, so a slight delay in communicating takes place. So slower message passing happens because the software application software has to first communicate with the server and then to the kernel space. And of course, there is a high complexity in maintaining, but we can see the modularity that has taken place. The server module is different, application module is different. So modularity has been maintained, and high memory usage also is needed because the server, as we have separated all those management files into the user space, we need to have a high memory capacity to store those files. Then the third one is exokernel. So exokernel, it is actually different from monolithic and microkernel in case of designs, where you can just see there we have the application softwares here, application software libraries, and also we have a library OS also. So this actually allows for greater flexibility, and performance is improved, and we can have a control mechanism which will advance the kernel execution. So the key characteristics are like resource exposures. We can see in exokernel architecture, and it has direct access to hardware resources. So it can access CPU, memory, and the IO units directly because it is available in the uh, user space. And this direct access enables application to manage these resources. So, but we had not found this in case of microkernel and monolithic kernel. So this libOS that will try to build a communication with the existing resources and the IO units. The protection and isolation, despite exposing resources directly to the applications, are needed. And these applications will run in separate address spaces, and they are so much required because they will prevent the unauthorized access and interferences. And exokernel, it also supports minimalism, like it provides only essential abstractions, and uh, s- the high level series are exempted, and the resource management will be taken to the user space liboses. So, so actually the kernel space has been minimalized. So it is trying to adopt very efficiently. And there is flexibility because exokernels offer unparalleled executions, and the resource management um, is being tailored actually. The developers, what they have done is for particular specific workloads, they can change the resource management, and they can tailor however they required based upon the applications, and the performance can be optimized, and resource can be utilized at a greater extent. So like disadvantages, I can just say it is very complex because as per the applications, the design can be, of course we have the flexibility, but the complexity increases as a change in application. So I can just say that there are some security issues also because the libOS is available in the user space. and compatibility because the developer can change the library files based upon the applications what need to be executed in the kernel space. So exokernels, it is like some shift in the operating system design. It has given certain flexibility, but yeah, performance-wise, when we say we are trying to expose the complete file management system files, the library files to the hardware resources because there is a direct connectivity between the user space and the hardware. So it is not compared to the microkernel and the monolithic kernel. This exokernel is not much in use. Uh, it of course, but it has surely influenced the operating system research and the development. So they have taken this exokernel as one of the research topic for shaping the future computing. But the maximum utilization of the architecture that happens in this real-time embedded system is microkernel. Task scheduling. Here, as many of the tasks they arrive, there are queuing of tasks. Like we can set certain priorities, but uh, initially those are queued, those are stacked somewhere, and the task scheduler is trying to allot the CPU time where whichever the computing entity may be, like whichever the CPU or the processors we have, its time is being allotted for those tasks. Here, in case of real-time operating system, we can have the task scheduling actually happens like it has to, whenever the task enters into the system, it has to check on whether the task is single task or the multitask, or what is the how the scheduler has to schedule the task, what kind of task it is, and is it time constraint task? What is the timer function for it? And how much resource allocation is required for that task? How the memory has to be managed for it? And what is the inter-task communication that need to be executed? So all these features need to be is required when we just when the real-time operating system approaches a particular task for its execution. So in case of task, when there is a task entry, then the task can have different states, like it can be in a run state, or it can be in a ready state, or a block state, or a dormant state. So scheduler, based upon different scheduling algorithms, it can either preempt the task or it can just leave the task as a non-preempt stages. Based upon scheduling algorithms, it can prioritize and prioritize the task, or it can schedule the task. It can provide the CPU time to the task. So as we saw that there are two main kinds of scheduling, preemptive scheduling and the non-preemptive scheduling. Here, preemptive scheduling is, suppose a particular task has high priority task. We have multiple tasks that are arriving, and one like we segregate those tasks based upon, we in the sense real-time operating system, the scheduler, it segregates the tasks based upon the priorities from high priority to the low priority levels. In such a case, say that one of the task is already in a running mode, then if there is an interruption that has to be done by the high priority task, then it will be interrupted and it will be moved, the task will be moved to the ready state by the scheduler, and the high priority task will be executed. So that is preemptive scheduling. But in case of non-preemptive scheduling, scheduler has more restricted control over task. Like we can think of like until the task completes its execution, the scheduler cannot interrupt. So it has some restriction to control the task. It can only start a task and it has to wait for the task to finish. Or suppose, like if the task voluntarily it returns the control to the scheduler, only then it can assign the CPU time to the next task. So a running task cannot be stopped by the scheduler. That is a disadvantage of non-preemptive scheduling. As we discussed, like in case of monolithical, like in super loop, when I said super loop, while one loop or the forever loop which we had, the task continuously executes. So, so in such a case, a hardware interrupt has to be initialized so that the task can be suspended and some interrupt service routines can be executed. Or if there is certain interrupt, then only it will assign the CPU time to the other task. So that actually we see in both general purpose and the real-time operating system. So here I have shown certain time slots for the CPU, and the tick time is 1 milliseconds, which is general for all the embedded system projects that we chose in case of Arduinos or the ESP32 system. I have taken here priority, only two priorities I have assigned, 0 and 1. And the operating system need to be executed. The scheduler has to keep scheduling the task based upon the priority and based upon the uh, clock, based upon the input, the operating system tick time. It the prioritized task will get executed. So here let us say that task A is getting executed. Initially it was ready and it is right now in the run mode. Then there was no high priority task, so task A is able to continue for the next tick. And suppose we have the high priority task, then it has to be preempted. But right now we don't have any task. In such a case, for 1 millisecond period, task A has put itself into a delay mode. It is right now idle. Maybe it has not completed its execution, but still it has put in a idle mode itself in a idle mode. Then task A will continue, and you can just see that task B and task C, they are high prioritized. They have the same priority. So task A has not completed its execution, but task B and task C are preempted. So they are given the CPU time slots. So task B and task C parallel, like they run one after the other, and later the task A will take. Suppose task A has to continue. Here I have shown in this case, like suppose we have a hardware interrupt. Then task B is interrupted. You can just see the task B is interrupted here. Task B also, in case of the operating system has to, the scheduler has to allow the CPU time for the interrupt service routine. So task B is not completed, but interrupt service routine will be executed. Then later it has allowed the task B to complete its execution after executing that subroutine. Now here task C was incomplete and task E the CPU time has been given to task C for the next tick of the operating system. And because task B and task C was high prioritized task, they have been executed one after the other. But task A, which was very low priority with priority 0, it has completed its execution at the last. So there are various task states, like we have task as soon as a task is created. So we have the state ready state. Then if we want to if the task has to be in executed, then it should be moved in the run state. Then then we suppose the task need to be blocked. Suppose the task is waiting for a queue, or if there is some semaphore, then if any blocking API function has been called during its run state, then the task move to the block state. And once it cannot directly communicate with like suddenly it can be after it cannot be moved to the run state, but it has to wait for the event. So it can the blocked task can be suspended also, or the ready task also can be suspended using here vtask suspend and vtask resume. It is the function that is used by a free RTOS supported by Amazon in 2017. It was released. So vtask suspend on vtask resume. When like vtask suspend function when it is executed, then the task moves to the suspended state. So no suspended task can be moved to the blocked state. It has to be first made ready and then move to the run state. So a suspended task can resume to run state only when it should say that it is ready to run. Only then it can be moved to the execution state. Here I have taken a particular case study where we have a real-time system that incorporates keypad, LCD, and a control algorithm, which I've chosen from a free RTOS documents, where we have the key handler task. So the key handler task is like user must get the visual feedback of each key when he presses within certain period of time. Like if the user cannot see that the key is pressed, uh, then it has been accepted within this period, like the key press has been accepted within this period. The software product will at best be awkward to use, like he'll not get to know whether the key is been pressed or not. So the task will move to the block state. If the longest acceptable period is within 100 millisecond, then it was acceptable. If it has taken more than 100 milliseconds, then actually the event is moved to the block state. So here you can just see that key handling is the continuous process, and it is implemented. Actually, this has been implemented in the infinite loop in this particular example. So we have a for loop where block to wait for a key press event. So it has been continuously waiting for the key to be pressed. Only when the uh, event takes place, only then it can come out of the block state. So then once it comes out of the block state, then only it can process the key press. Right. So these two events are included in this key handler task. And another task is V control task. Control task means here we like let us assume that a real-time system is performing certain control functions, and it is relying uh, on digitally filtered inputs from the sensors. Then these data need to be sampled, it has to be filtered, and it has to execute some control cycle to handle those data inputs, the sampled inputs for every 2 milliseconds. So for correct operation of the filter and the sampling to happen at a regular intervals, then it should happen because the delay, suppose let us say that it should happen in 0.5 milliseconds. It's not mandatory, it's an example, it is like 0.5 milliseconds. So, so in such a case, this particular code says that it is also a for loop. It's an infinite loop where we have the delay waiting for 2 milliseconds since the start of the previous cycle. And we have the sample input from the we have the input from the sensor already, that delay, whatever we have used, it is to accept the input, fetch the inputs. Then those inputs need to be sampled, filter the sampled input, perform control algorithm, and output the results. So these are the set of process that need to be executed within this control operations. So two tasks we have. One is key press and the other one is control task. So now if we just check on this, RTOS, this is how actually the scheduling has taken place for those two tasks. Uh, Here the blue arrow, what you see is a key press event, and the red arrow, which you see is a timer event. So we have two tasks, V control task and V key handler tasks. So the time slots, like at the start, neither of the two tasks are able to run, right? So initially it is like idle. So we have V control task, which is waiting for the correct time to start. It has not started at all. You can just see the V control task. It has started at T3, but initially it has not started because it has to fetch the data from what I have taken, like from any IoTs, it has to fetch the data. So it has to keep waiting for 2 milliseconds in such a case. But V control task is waiting for the correct time. So where when it has to start, when the new control cycle has to start, and key handler task is waiting for a key to be pressed. So in case so at T1 time period, none of the task has been executed. So processor time is given to the RTOS is totally idle. At T1, you can see a key has been pressed, right? The blue arrow here, it says that it is the key has been pressed. So now when the key has been pressed, key handler task has to be executed. That's because it has a highest priority. Otherwise, the task will move to the block state, right? So it has the highest priority. So compared to the idle task, the key handler task has the highest priority. So the key handler task will be preempted right now. So idle task was running, but the key handler task has the highest priority. So the key handler task has been executed at T1. And at T2, you can see that the key handler task has completed its processing. And let us say that now that key handler task, I'm just taking an example, that it has moved to the updating of LCD or something else. So it cannot continue until another key has been pressed. So what it does, it has to suspend itself, and the RTOS idle task is again resumed. So when the naturally when the task suspends, so the idle it moves to the idle state. So it suspends. It is been it until it resumes, it cannot be made to execute. So idle task will be running right now. So at T3, a timer event indicates that it is time to perform the next control cycle. So at T3, the V control task is executed. V control task has the highest priority as per our assumption. So V control task has highest priority and idle task has the lowest priority. So at T3, the control cycle is getting executed and it has the highest priority, and that task is scheduled uh, by the processor time immediately. So between time T3 and T4, you can observe, like, once the control task has been executed, the data is being sampled, it has been filtered, everything. Once all those process has been done, now the control task will wait for the next data to be displayed on the LCD. For that, what we have to do, we have to press the next key, right? So it keeps waiting for the key handler task. Um, uh, so now it is a time for the key handler task to execute once, if it has like it was suspended and it has moved to the idle task was executed. There was a delay, and now the key handler task is being executed. Once the control task has executed, it has sampled the data, everything. It now has the control over the LCD. And right now, it is able, whatever the key has been pressed, that can be displayed on the LCD. So control task has fetched all the data. Now it has to write back. Right, it has the instruction decoding has been happened, right? It has to be processed, and now it has to write back to the LCD. So to do that, it has executed for between T3 to T4 time period. Later, key handler task has resumed back, and its execution takes place. So at the T4, at the T4, here the key handler task has been executed, and again the task has certain delay, and idle task has been executed. You can just see that how the control task, the high priority task uh, has been given the CPU time based upon its priority. So RTOS has itself created a task, right? It has created, like, we have not imposed idle task. We had written only the key handler task and the control task. But now what RTOS is doing for the context switching, it is trying to impose certain idle task, right? To fetch the data or to decode it. So for that purpose, a small duration of time, it wants to put the task into sleep mode. So the RTOS idle task is always in a state where it has to be where it is able to execute. These are some examples of the real-time operating system, um, like air traffic control, telecommunication, weapon guidance systems, medical diagnostics, automatic engine control system, real-time database, and the Mars rovers recent, just 2 3 years back, which has been put on Mars by the ISRO. So these are certain examples which I listed. So the scheduling concerns which we should have here is like whether the task is like which type of scheduling algorithm it has to run. Right, we have number of tasks as this I have spoken already. Any real-time operating system need to know how many number of tasks need to be run, how many resource requirements are there, what is the release time, what is the execution time, is there any time constraint, has the deadline to be met. All these managing system has to be carried over by the operating system. But to do that, uh, to accommodate all these requirements, it should also, like, we need to have multiple scheduling algorithms, right? It may be round robin scheduling, released recently used scheduling algorithms, or it may be uh, first come first, like all many different scheduling algorithms are there, where real-time scheduling is classified based upon offline and online mode. So in case of online, we have static priority and the dynamic priority that exists. In case of static priority, we have preemptive and non-preemptive classifications, but dynamic priority, it is plan-based, uh, and uh, and the best effort the task shows. So offline scheduling pre-runtime is also called as pre-runtime scheduling. Here it generates scheduling information prior to system execution. And of course, it is a deterministic system models. It is totally based upon the task release time, time constraint, deadlines it has to be met, and the execution which has to be done, execution which has to be done. If any parameters changes while executing this task, then the complete task policy has to be recomputed. That's a disadvantage what we find here. In case of online scheduling, the number of tasks, the type of tasks, and the associated parameters with the tasks, this will not be known at all. So it is like it is not well planned, like the offline task. So it's totally dynamic in nature. So scheduling must accommodate dynamic changes. So here also one thing which can be kept static is priority can be made certain task static by the scheduler, and this also is for limited time period, but dynamic priority, we want the task to be executed for dynamic priority. So here a task is released to execute every 5 milliseconds in case of non-preemptive, as we have seen in the previous example. Priorities, it depends upon how much memory space you're using. Memory space in the sense, you need to assign in the lookup table like what priority you give. Here, I've shown it as 1 to 99. The highest ones need not root at all. So, there are certain conflicts with the traditional kernel scheduling, like deadlines will be met, but the task fair execution does not happen. So these are the conflicts which has to be, there is always a trade-off. So such conflicts has to be um, overcome, or certain design has to be changed so that some fair execution, like scheduler, that's why the scheduling algorithm optimizations will be done. For the best scheduling algorithm has to be designed which can meet both deadlines, timing constraints can be met, and it can fairly execute all the tasks based upon the timing constraint. No, there should not be any system call which will be left unattended. That is actually is a need of the hour. So, for example, if a user access the kernel, we cannot guarantee whether his task will be run for 1 second or it will be run for 5 second intervals, because the scheduler, the person who gives the time slots based upon the execution time or the resource requirement for the task. So that time period. So that time period, that latency, what we see because of the time interval which is changing, dynamically changing, that can be efficiently done if we design the scheduling algorithms, not designing, sorry, if we what I can say, if we optimize the scheduling algorithms very efficiently, then naturally it can check on all the parameters of the tasks management system, and then a fair level of task execution can happen. The CPU time allocations can be done very fairly. There are certain challenges that exist. So, like in case of Linux, it uses proportional sharing. So here the answer is highly dependent on other system activity. Right. So if another process boots its priority, then whether this particular proportional sharing task has to be preempted or what? What if another process is starving? Such a challenges, like that's what I said. The fair execution it is taking time to execute the CPU time. Sorry, execute the what task at a fair interval of time. what are the goals that need to be achieved for predictable execution? So to overcome those concepts, what the challenges which we have seen in the previous slide. We are supposed like one thing is we can have an ideal task, fix a time slot for each task, and that has to execute within that stipulated time period. And but in real world that doesn't happen. So we have to preempt the task based upon the priority, and then migrate the task which was in the running mode to the next time interval. So in real world, actually, the second one, what you see, this is under execution. So other sources of uncertainty and solutions also exist. Like while the task is executing, there may be certain interrupts. And of course, we can mask some interrupts, but some hard interrupts need not be masked, should not be also. Like there can be certain migration of the task. In such a case, based on the priority, if you want to pin the task to certain course, if you have multiple course, then you can pin a task that it has to execute prior to any other low prioritized tasks. So there may be some OS latencies, jitter, and kernel non-preemptibility that exists. So these are the challenges which the real-time operating system faces, and it has to support like we need it has to support the real-world task to be executed even when there is certain dynamic changes. So I have listed few scheduling algorithms, like it can be first in, first out scheduling or round robin scheduling, preemptive fixed priority scheduling. Most frequent first scheduling algorithm can be used. Earliest deadline first scheduling algorithms. There are various scheduling algorithms that are available, and based upon that, the task scheduling can be done. Um, One is FIFO scheduling, first in, first out scheduling. Here you can just see that the first MQ task of highest priority will be executed for the completion. And um, whichever task relinquishes a processor, when it completes, it will complete and it will yield, and also it will move to the block state. Only a higher priority task that can preempt, right? It can preempt, and all the others will be starved as it runs. So task 1 in this case has the highest priority compared to task 3. So task 1 will execute, then task 2 and task 3. So until task 1, like it is in a FIFO, like first the task 1 has entered first. So task 1 will be executed first, and then based upon the FIFO, in the FIFO, how the task has been entered, based upon their allocation, the tasks will be given the CPU time. In case of round robin scheduling, all the tasks will be given equal number of time slices, and so they will have equal priority. So they rotate through all the tasks. Each task gets a fixed time slice. So here I have shown 3 tasks. Task 1, task 2, task 3 had suppose each task had to be executed in 20 milliseconds. Then 5 milliseconds is allocated for each. The task timings may change. So task 1, 5 milliseconds of CPU time has been allocated for task 1, then task 2 and task 3. So next again the same task 1 will appear after task 3. So this is how the round robin scheduling takes place. One after the other, the task gets executed based upon round robin fashion. So in this case, task has equal priority, preempt each other after time slice expiration. So like See, in case of preemptive fixed priority scheduling, which all the we have seen an example already. But here, see, the highest priority task is executed first, then it moves to the idle task, and then the next highest priority will execute. So here you can just see that the low priority task and the high priority jobs both have arrived together. In such a case, the low priority task has to be pushed to the next cycle. So this is what happens. So until the high priority task executes, the low priority task cannot be executed. So this is how the scheduler manages. Then here again, the low priority task has not completed its execution. Meanwhile, for the next tick, the high priority job has been arrived. So we have to give the CPU time for the high priority task. So in such a case, only some you can just see this is what the time is required to complete the low priority task. But the task execution has not been completed. So after the high priority task execution, the low priority task will resume its execution. And the second task which was incomplete, that will be executed after the low priority task execution. So this is how the task execution has taken place in preemptive fixed priority scheduling. Now here the other kind of scheduling algorithm is rate monotonic scheduling. In this case, a priority is assigned based on the inverse of its period. Now, the shortest period will have the highest priority. Means if the task duration is very less, then surely that will be given the highest priority. The longest period task will have the lowest priority. So in this case, you can just see that P1 is assigned the highest priority than P2. So P1 will be executed first. So like the deadlines are decided based upon the duration of the tasks. Suppose any missed deadlines we have within rate monotonic scheduling. And now, see here, we have executed P1, P2 tasks, but the P1 task might not have completed its execution. There are no chances actually that the deadlines will be missed, but in case if the task moves to ideal state or the block state, then there are certain chances that the task may miss particular deadlines. uh, Earliest deadline first scheduling. Here, suppose task 1 has deadline of 5 millisecond and execution time is 4 milliseconds. Similarly, task 2 has 8 milliseconds and 3 milliseconds. Task 3, let us say it has 12 and 2. So theory exists to analyze such a system. So task 1 will be executed first. uh, First, so for almost 9 milliseconds. Then the task to, like if at all we have actually that in case of non-preemptive, it has to be executed for completely 4 milliseconds. So here also we can just see that the task 1 is executed for 4 milliseconds, and the rest 1 milliseconds can be utilized for task 2. Because task 1 execution has been completed within 4 milliseconds. So from 4 milliseconds onwards, the task 2 execution takes place. Instead of utilizing, instead of pushing the task, a new task called as idle state, it is better to make the task to execute. But practically, it is very difficult because such a type of abrupt context switching happening is very difficult. But this is the theoretical expectations what we have. Uh, Here, in increasing the execution time determinism means, suppose we are using a simple pipelining for instructions from each task, and this avoids, so naturally when we use the pipelining methodology for instructions, then the complexity will be reduced. So in such a case, the task execution can happen simultaneously. And here we have to here we have two categories like fine-grained time sharing of the processor and interleaving order of issued instruction from the task, which reduces the global processor stalls and which is caused by data and control hazards. So increasing the processor availability by reducing context switching and operating system overhead using an operating system co-processor can be done. But what we insight on this is push the scheduling logic into hardware. So here the memory space is more required, and the scheduler itself is a separate entity in such a case. If we are able to do that, then again the scheduler can be made much optimized. So the execution time can be reduced if we are moving this particular piece of software into a hardware. Now I don't think this is needed. Now here we have a particular processor. You can just see that every processor, like co-processor, will have a real-time clock unit. So we'll have the configuration and data register banks that are available, and exception general unit also. The task handling unit is separately available, and semaphore handling unit also is available. So the real-time clock unit, it decides which data from the register bank has to be the real-time clock unit. It will give the control. It will specify like that when the task has to be executed. It is a continuous clock which is available. So task handling unit, it will decide which data has to be given the CPU time. Which task is a periodic event, or which has to be preempted, whether the interrupt request executes. All this will be handled by the task handling unit. And semaphore handling unit also is being separated. If at all the API event has been occurred, like that block has been executed, then the task will be made to move to the block state. So this is how the coprocessor which is used in real-time operating system looks like, which works on real-time clock unit. So the real-time scheduling is based on assumptions, like it can be periodic task, whether the priorities are known, whether the runtimes are known. So it is assumptions that are made by the scheduler. What happens when we don't know how long something will execute? So in such a case, naturally the execution time, I don't know. So runtime will vary, but the deadline has to be met. So in such a case, it is very difficult to uh, guarantee. So we need to have the task handling unit to be very strong, the scheduler to be very strong. So a large effort has to be put on designing of this scheduling algorithms. So here we have observed that the execution time is being reduced compared to the possible execution times. You can just see that distribution of execution time, how it has happened. As per the static analysis, the time may be the time required for the execution, it may be large, but the possible execution time which has been desired by the designer, that is some stipulated fixed time, but uh, but but the scheduler might have imposed because of some known priorities or known run times, which it has accepted, which it has assumed. Based upon that, the execution time which has been measured, it has been reduced. But the data, what the result, I can say, the result which is obtained in in this execution period, it may be more efficient, but it need not be efficient also, but sometimes it may be efficient or it may not be also. So dynamically it may change. So I am just stressing on this particular point that we require for a real-time systems efficient scheduling algorithms, efficient task handling unit that uh, can avoid the catastrophes and meet all the deadlines at totally 100%. So criticality, mixed criticality, surely embraces this uncertainty. We can just say that for a real-time system, we know that any answers that we get late, then it is a wrong answer, we say. Means even if it is able to compute, execute, and provide the correct answers after long duration of time also, we cannot accept the data because it has not met the time constraint. It has not executed within the time period. Execution has happened, but it has taken a long time period. But there are possibility that within the stipulated execution time constraint also, the result may not be proper. So such a criticality exists, and we have to overcome that. So I just want to bring to the last concept uh, of my topic, robust mixed criticality, where we have three modes, where the normal mode, resilient mode, and high DAL mode, where robust task is one that can safely drop a non-started job. A fault is measured when one task overruns uh, the clock time period. So an error is registered when one or many tasks fail with their timing requirements. So the system is said to be resilient only when the task employs graceful degradation. Uh, we can say that uh, we can increase the execution with certain changes in the control of the robust task. In order to cope up with one or many faults, we have to aim to avoid errors. So, uh, the error handling capability also should be thought about. So always a normal mode task, if the task is at the normal mode, then it will be executed within the stipulated time period. If we expect that there is certain error which has been registered, then it can move on to resilient mode. Then the error handling capability task can be executed. Meanwhile, the task is put into the idle state. Uh, Later, it will be resumed back. So the scheduler has to decide how robustly the task has to be executed. So to avoid the criticality. So these are the references which I have taken. We have most of the diagrams that I have chosen is from free RTOS documentation. from the website. Free RTOS documentation is Free RTOS is a real-time operating system which can be used on ESP32 and all. So some projects can be done on that. So one can just go to that website and have a look on it. Any queries if you have?
Thank you, ma'am. So I request from participants side if there are any queries. So please unmute yourself and you can go with the questions. Any queries?
It's late, so most of the participants are.
Okay. Ma'am, thank you, madam, for the enlightening session. We truly appreciate the time and valuable insights you have shared with us. Thank you, ma'am. And I request all the participants to fill the Google form which is shared in the WhatsApp group.
I would like to thank SSIT Tumkuru for providing an opportunity to share my thoughts on a real-time operating system. I thank Dr. Komla Madam for inviting me to the session. Thank you so much.
Thank you, ma'am. We were delighted to have you with us. Thank you so much.
Thank you, ma'am.
Thanks to all the participants and good night. So once again, I'll request all the participants to fill the Google form shared in the WhatsApp group. Thank you.